So here's something worth thinking about as you settle in tonight. Right now, wherever you are, there's a machine nearby that's following instructions. Maybe it's the thermostat on your wall, reading the temperature in this room and deciding, dozens of times a minute, whether to push warm air through the vents. Maybe it's the refrigerator in your kitchen, cycling its compressor on and off to hold the inside of the cabinet at precisely the temperature you set and then forgot about. Maybe it's your phone, adjusting its screen brightness based on the ambient light, so smoothly and so quietly that you've never once thought about the fact that something is making that decision for you. And if you flew here from somewhere, think about what happened on that flight. The autopilot, from shortly after takeoff to just before landing, was flying the airplane, making hundreds of tiny adjustments to the control surfaces every second, maintaining altitude, heading, speed, all while compensating for wind gusts and turbulence and the slowly changing weight of the aircraft as it burned fuel. And the language that autopilot speaks, the instructions it follows, the mathematical framework it uses to make those decisions, has a history that stretches back over 100 years, through some of the most fascinating twists and turns in all of engineering. These machines are all doing something. They're all following a set of instructions. And the strange thing, the thing that most people never stop to consider, is that none of these machines understand a single word of any human language. Not English, not Mandarin, not anything you or I would recognize as communication. They operate in voltages, in currents, in the opening and closing of tiny switches millions of times per second. And everything, literally everything that makes the modern world function, from the water pressure in your pipes to the flight path of every aeroplane overhead, depends on our ability to translate what we want into something a machine can act on. That translation, that act of taking a human intention, something as vague and fuzzy as "keep this room comfortable," or "don't let this chemical reactor overheat," or "land this airplane safely," and converting it into precise, unambiguous instructions that a machine can execute without hesitation. That's one of the most important and least talked about problems in all of engineering. And the story of how we solved it, how we went from having no way to talk to machines at all, to having entire vocabularies and grammars and syntaxes designed specifically for that purpose. That story is genuinely fascinating. It stretches across about 150 years. It involves electricians and mathematicians, telephone operators and rocket scientists, factory workers in Detroit, and software engineers in Silicon Valley. And it's still unfolding right now, in ways that are raising questions nobody quite knows how to answer. So tonight, we're going to walk through that story together, slowly and carefully. How did we learn to talk to machines? What languages did we invent and why? What happens when the language breaks down, when the machine misunderstands, or when we ask for something we didn't quite mean? And the question that's becoming more urgent with every passing year: what happens when machines start finding their own solutions? Solutions that work, but that we can't fully read or interpret, in a language that no human being designed. These are questions that touch your life every single day, whether you realize it or not. Because every time you step into an elevator, every time you drive across a bridge, every time you flip a light switch or open a faucet or board an airplane, you are trusting that someone, somewhere, found the right words to tell a machine what to do, and that the machine understood. So let's start at the beginning. Let's start in a world where machines had no language at all, where the only way to program anything was with your hands, a pair of pliers, and a whole lot of copper wire. To really understand why the languages we use to talk to machines matter so much, you have to first understand what the world looked like before those languages existed. And that means going back to a time when the word programming didn't mean writing code on a screen. It meant physically connecting wires, bending copper, bolting things to metal rails, making and breaking electrical connections with your actual hands. Let's go back to roughly the 1920s and 30s, the era when factories were growing larger, faster, more complex. The assembly lines that Henry Ford had pioneered were spreading everywhere, and with them, came an enormous practical problem. How do you control all of this machinery? Think about what a factory floor looked like in those days. You've got conveyor belts moving parts from one station to the next. You've got presses stamping metal, drills boring holes, welders joining pieces, paint sprayers coating finished parts. And all of these things need to happen in a specific sequence, at specific times, with specific conditions met before the next step can begin. The conveyor can't move until the press has finished its stroke. The drill can't start until the part is clamped in place. The paint sprayer can't fire until the part has cooled enough to accept the coating. Someone needs to coordinate all of this. And in the early days of industrial automation, that coordination was done with relays. Now, if you've never seen a relay up close, the concept is beautifully simple. A relay is just an electrically operated switch. You send a small electrical signal to it, and that signal energizes a coil, which creates a magnetic field, which physically pulls a metal contact from one position to another. When the contact moves, it either makes or breaks a circuit somewhere else. So a small signal in one place can control a much larger signal in another place. And you can chain relays together. The output of one relay becomes the input to the next, which triggers the next, which triggers the next. You can build sequences this way. If relay A is energized and relay B is energized, then relay C turns on, which starts the motor, which moves the conveyor. If the conveyor reaches a certain position, a limit switch closes, which energizes relay D, which turns off the conveyor and starts the press. Each relay is making a simple decision, on or off, yes or no. But when you wire hundreds or thousands of them together in the right configuration, you can orchestrate an entire production line. The relays are, in a very real sense, the machine's brain. The wiring between them is the program. And to change what the machine does, you change the wiring. Here's what that actually looked like in practice. Imagine a room, not a small room, a big one. Floor to ceiling, the walls are covered with metal cabinets, and inside those cabinets are rows upon rows upon rows of relays. Hundreds of them, sometimes thousands. Each one mounted on a metal rail, wired to its neighbors with bundles of colored wire so thick and so tangled that they looked like the root system of an old tree that had been ripped out of the ground. The room hummed, literally hummed, because every time a relay switched, its armature would click, and with hundreds of them clicking at different moments, the whole room filled with this constant rhythmic chattering. Factory workers who spent time in relay rooms described the sound as almost alive, like being inside the ribcage of some enormous mechanical animal. And the thing about these relay panels is that they worked. They genuinely worked, and they ran factories all over the world for decades. The automobile industry was built on them. The food and beverage industry was built on them. Telephone switching networks, which had to route millions of calls automatically through vast webs of interconnected lines, were essentially enormous relay computers. The clicking of relays was the sound of the 20th century's infrastructure operating. There were people who spent their entire careers inside these relay rooms, and they developed an almost intuitive sense for the health of the system from its sound alone. An experienced relay technician could walk into a room, listen to the pattern of clicking, and tell you whether the system was running normally or whether something was off. A relay that was sticking would produce a slightly different sound. A relay that was chattering, switching on and off rapidly because of a wiring fault, had its own distinctive buzz. These technicians were, in a very real sense, listening to the language of the machine. And the machine spoke in clicks. But relay panels had problems. Deep, fundamental problems that grew worse as factories grew larger and more complex. The first problem was sheer size. As the logic you needed got more complicated, the number of relays grew and grew. A moderately complex production line might need 1,000 relays. A large one might need several thousand. Each relay needed power, Each relay generated heat. Each relay took up physical space. The relay rooms got bigger, the wire bundles got thicker, the electrical bills got higher. The second problem was reliability. Relays are mechanical devices. They have moving parts. Moving parts wear out. A relay might be rated for 1 million operations, which sounds like a lot until you realize that a relay switching once a second will hit 1 million operations in about 11.5 days. In a factory running 3 shifts, relays were failing constantly. And when a relay failed, everything downstream of it could stop working. Finding the failed relay in a panel with 2,000 of them, buried behind bundles of wire in a dimly lit cabinet, was a skilled trade in itself. Maintenance electricians who could quickly diagnose a relay panel failure were worth their weight in gold. But the third problem was the really killer, and it had to do with flexibility, or rather, the complete absence of it. Here's the thing about a relay panel. The program, the logic that determines what the machine does, is physically embedded in the wiring. If you want to change the logic, you have to change the wires. You have to physically go into the cabinet, pull out wires, reroute them, add new relays, remove old ones, and then test everything to make sure you didn't accidentally disconnect something that still needed to be connected. And in the automotive industry, where this problem was most acute, model changes happened regularly. Every year, the car companies would introduce new models. New models meant new parts. New parts meant new production processes. New production processes meant rewiring the relay panels. Entire panels had to be redesigned, rebuilt, and tested from scratch. This took weeks, sometimes months, and during that time the production line was down. No cars were being made. The cost was enormous. General Motors, in particular, was spending staggering amounts of money on this annual rewiring ritual. By some estimates, the annual model changeover at a large GM plant could require the rewiring of thousands of relay connections, taking teams of electricians weeks of overtime work. During that time, the production line was silent, no cars rolling off the end, no revenue. Every day of downtime was enormously expensive, and the irony was that the new logic wasn't usually radically different from the old logic. Maybe a few sequences changed, maybe a timing was different, maybe a new station was added to the line. But because the program was embedded in the physical wiring, even small changes required physical modification. It was, if you think about it, as if every time you wanted to edit a paragraph in a document, you had to physically retype the entire document from scratch. The content was locked in the medium. You couldn't change one without changing the other. They needed a better way. They needed a system where you could change what the machine does without physically changing the wires. They needed the program to live somewhere other than in the copper connections between relay contacts. They needed, although nobody used this word yet in this context, software. And in 1968, a team of engineers at a company called Bedford Associates in Bedford, Massachusetts, led by a man named Dick Morley, gave them exactly that. Now, Morley is a wonderful character in this story. He was an engineer's engineer, practical, inventive, a little iconoclastic. He worked on various electronic control projects throughout the 1960s, and he understood both the world of digital electronics and the world of factory automation, which at that time were almost entirely separate universes. The electronics people thought in terms of logic gates and flip-flops and binary arithmetic. The factory people thought in terms of relays and motor starters and limit switches. Morley saw the bridge between them. The specific catalyst was a set of requirements that came from General Motors' Hydromatic division, the group that manufactured automatic transmissions. They issued a specification for what they wanted: an electronic replacement for relay panels that could be programmed by plant electricians, that could survive the harsh factory environment, vibration, temperature extremes, electrical noise, and that could be modified easily when production requirements changed. That specification, sometimes called the GM spec, is often cited as the birth document of the PLC industry. Morley and his team at Bedford Associates built the Modicon 084. The name Modicon stood for Modular Digital Controller. It was the world's first commercially successful programmable logic controller, the PLC. A device that could replace an entire room full of relays with a single box. A device whose program lived not in wires but in electronic memory. A device whose behavior could be changed not with pliers and copper, but with a keyboard and a screen. There's a detail about the Modicon 084 that I find particularly telling. The original unit used magnetic core memory, the same kind of memory used in early computers. And one of the reasons they chose core memory was that it was non-volatile. It retained its contents even when power was lost. In a factory, power outages happen. And if your PLC lost its program every time the power flickered, you'd have a very unhappy plant manager. The choice of memory technology was driven not by what was theoretically best, but by what would survive the real conditions of a factory floor. That's a sign of engineers who understood their users. But here's the beautiful part. The part that made the PLC succeed where other computing approaches had failed. The language they chose for this new device wasn't some exotic programming syntax invented by computer scientists. It was something far more clever than that. It was designed to look exactly like the thing it was replacing. It was designed so that an electrician who had spent 20 years reading relay schematics could sit down in front of this new device and feel, immediately, that they already knew how to use it. And that language, that brilliant, pragmatic, deceptively simple language, is what we need to talk about next. Because it's still the most widely used programming language in industrial automation to this day, more than half a century after it was invented. And the reason it endures tells you something really important about how languages succeed and fail, not just in engineering, but everywhere. So, the PLC exists. It's the late 1960s, early 1970s, and factories are starting to replace their relay panels with these new electronic boxes. And the first and most important question that the people building PLCs had to answer wasn't a technical question at all. It was a human question. It was this: who is going to program these things? Now, think about who worked in factories at that time. You had mechanical engineers who designed the production equipment. You had electricians who wired and maintained the relay panels. You had maintenance technicians who fixed things when they broke. And you had plant managers who cared about one thing above all else, which was keeping the production line running. What you did not have in most factories in 1970 was computer programmers. Computer programmers existed, of course. They worked at universities, at aerospace companies, at large corporations with mainframe computers. They wrote code in languages like Fortran and COBOL, languages designed for scientists and business analysts. But a typical auto plant in Detroit? There was no one there who knew Fortran. There was no one who understood loops and subroutines and variable declarations. And even if there had been, the language of Fortran had nothing to do with the language of the factory floor. The factory floor spoke a different language entirely. It spoke in terms of contacts and coils, normally open, normally closed, series circuits, parallel circuits, motor starters and limit switches and solenoid valves. This was the vocabulary that every electrician understood. They could read a relay schematic the way you and I read a sentence. They could look at a diagram and immediately know, if this switch closes and that switch closes, then this motor will start. It was second nature to them. It was the language they thought in. And the genius of the PLC's creators, the insight that made the whole thing work, was that they didn't try to teach electricians a new language. Instead, they made the machine speak the language that electricians already knew. The language they created is called ladder logic. and the name comes directly from what it looks like on a screen, or originally on a programmer's terminal. Imagine two vertical lines, like the rails of a ladder. Between those rails, running horizontally like the rungs, are the logical conditions and outputs that make up the program. On the left side of each rung, you have contacts. These represent inputs, conditions that are either true or false. A switch is closed or it isn't. A sensor is tripped or it isn't. A button is pressed or it isn't. On the right side of each rung, you have coils. These represent outputs, things you want to turn on or off. A motor, a valve, a light, an alarm. And the rule is simple. If all the contacts on a rung are satisfied, if the logical conditions are met, then the coil at the end of the rung energizes. If any contact in series is open, the coil stays de-energized. Contacts in series mean and. Both must be true. Contacts in parallel mean or. Either one can be true. Let me give you a concrete example, because this is the kind of thing that becomes clear the moment you see it in action. Imagine you have a machine with a start button, a stop button, and a motor. You want the motor to start when you press start, keep running after you release the start button, and stop when you press stop. In relay logic, you'd wire this with a seal-in circuit, where the motor contactor has an auxiliary contact that keeps the circuit energized even after you release the start button. And the stop button, wired as a normally closed contact in series, breaks the seal-in and stops the motor. In ladder logic, this looks almost identical. One rung. The start button as a normally open contact. In parallel with it, an auxiliary contact from the motor output, the seal-in. In series with both of them, the stop button as a normally closed contact. And at the end of the rung, the motor output coil. That's it. One rung, 5 symbols. And an electrician who sees it immediately knows what it does, because it's the same circuit they've been wiring with physical relays for years. The language maps directly onto their experience. Beyond simple on-off logic, ladder logic also supports timers and counters, which show up constantly in industrial automation. A timer might delay the start of a motor for 5 seconds after a pump starts, giving the system time to build pressure. A counter might count the number of parts that have passed a sensor and trigger an action every 50 parts. These functions, timers and counters, are the bread and butter of sequential automation, and in ladder logic, they appear as special function blocks that you wire into your rungs just like any other element. If you've ever seen an electrical schematic for a relay circuit, this is going to look almost identical. And that's entirely the point. An electrician could look at a ladder logic program and see immediately the same familiar pattern of contacts and coils they'd been working with for their entire career. The symbols were the same. The logic was the same. The only difference was that instead of physical relays wired together with copper, these were virtual relays, existing as instructions in the PLC's memory. And here's what made that difference so profound. To change the program, you didn't need pliers, you didn't need wire, you didn't need to shut down the panel, pull bundles of cable, and rewire connections for weeks. You sat at a terminal, moved your cursor to the rung you wanted to change, added or removed a contact, and downloaded the new program to the PLC. Minutes instead of weeks. And the wires in the cabinet, the physical connections between the PLC and the actual sensors and motors out on the factory floor, those stayed exactly the same. You changed the program, not the wiring. Think about what that means for the annual model change at an auto plant. Instead of rewiring thousands of relays, you reprogram the PLC. The same hardware, the same wiring, the same physical infrastructure, but different behavior. Different sequences, different timing, different logic. All changed through software, through a language that the people on the factory floor could already read. Now, I want to stay with ladder logic for a while, because it tells us something really important about how languages work. not just programming languages, but all languages. Ladder logic succeeded not because it was the most powerful or the most elegant way to express logic. By the standards of computer science, ladder logic is crude. It doesn't have sophisticated data structures. It doesn't handle complex mathematics gracefully. It's clumsy at text processing. A software engineer looking at ladder logic for the first time might wonder how anyone gets anything done with it. But ladder logic wasn't designed for software engineers. It was designed for electricians. And for electricians, it was perfect. Because it mapped directly onto the mental model they already had. They didn't need to learn to think differently. They just needed to learn a slightly different way of expressing what they already thought. This is a deep insight about the design of any language, human or machine. The best language for a given purpose isn't necessarily the most powerful one. It's the one that fits the way its users already think. A language that requires you to completely rewire your mental model before you can use it, no matter how powerful it might be, faces an enormous adoption barrier. A language that meets you where you are, that builds on what you already know, that makes you feel competent from the first moment you encounter it, that language spreads. It gets used. It becomes a standard. And ladder logic became the standard. It spread from General Motors to the rest of the auto industry. From the auto industry to food and beverage, to pharmaceuticals, to oil and gas, to water treatment, to building automation, to essentially every industry that used machines. By the 1980s, PLCs running ladder logic were everywhere, and by everywhere I mean everywhere. The traffic light at the intersection near your house, very likely controlled by a PLC running ladder logic. The elevator in your office building? PLC. The conveyor belt at the airport that moves your luggage? PLC. The ride at the amusement park? PLC. The system that treats the water coming out of your tap? PLC. And most of these systems, even today, are still programmed in ladder logic. Which means that a language designed in the late 1960s to help electricians in Detroit reprogram assembly lines is right now, tonight, controlling infrastructure that you depend on every single day of your life. But ladder logic, for all its elegance and all its success, had limitations. As the problems that PLCs were asked to solve grew more complex, as the processes they controlled grew more sophisticated, as the people programming them started to include not just electricians, but also chemical engineers and software developers and process control specialists, the limitations started to matter. And the question arose, if one language isn't enough, if different kinds of problems and different kinds of people need different ways of expressing instructions to a machine, then how many languages do you need? And what should they look like? That question would eventually produce an answer, an international standard, 5 programming languages, each designed for a different kind of thinking, each suited to a different kind of problem. And the story of how those 5 languages came to be, and why each of them exists, is a story about the different ways that human minds approach the act of telling a machine what to do. By the late 1980s, the world of industrial automation had a problem that was, in a way, a problem of success. PLCs were everywhere. They were manufactured by dozens of companies. Allen Bradley, Siemens, Mitsubishi, Omron, ABB, Schneider Electric, Beckhoff, and many more. Each of these manufacturers had developed their own programming environment, their own version of ladder logic, their own extensions and add-ons and proprietary features. And while the basic concept of ladder logic was similar across all of them, the details differed enough to be maddening. A program written for an Allen Bradley PLC couldn't simply be loaded onto a Siemens PLC. The syntax was different. The addressing schemes were different. The way you handled timers and counters and data types, all subtly different. If you were a controls engineer who knew one manufacturer's system, moving to a different manufacturer meant learning a whole new set of conventions. And if you were a plant owner with equipment from multiple manufacturers, which was extremely common, you needed specialists for each one. This was like a world where every telephone company used a different language for their switching equipment. The phones all did the same thing. They made calls. But the engineers who maintained them couldn't move between systems without extensive retraining. Something needed to be standardized. In 1993, the International Electrotechnical Commission, the IEC, published a standard called IEC 61131, Part 3. And this standard did something ambitious. It defined not one, not two, but 5 programming languages for PLCs. 5. And the reason there were 5, rather than one universal language to rule them all, tells you something very important about the nature of communication with machines. The 5 languages exist because different kinds of problems are best expressed in different ways, and different kinds of engineers think in different ways. Forcing everyone to use the same language would have been like forcing poets, mathematicians, architects, and musicians to all communicate using only spreadsheets. You could probably do it technically, but you'd lose an enormous amount of nuance and efficiency along the way. So let's walk through all 5, because each one reveals a different facet of how humans think about instructing machines. The first, and we've already spent some time with it, is ladder diagram, usually abbreviated LD. This is our old friend ladder logic. It's the visual relay schematic language that electricians already knew. Under the IEC standard, the basic concepts were formalized and standardized. Contacts on the left, coils on the right. Series means and. Parallel means or. The specific symbols were defined so that a ladder diagram written to the IEC standard would look the same regardless of which manufacturer's PLC it was running on. Ladder logic remains the most common PLC programming language in the world. If you walk into a factory, any factory, and look at the PLC program, the odds are very good that you're going to see ladder logic. It's especially dominant in discrete manufacturing, the kind where you're making individual things, cars, appliances, electronics, and where the logic tends to be about sequences of on-off decisions. Is the part in position? Yes or no. Is the clamp closed? Yes or no. Has the press completed its stroke? Yes or no. For this kind of binary sequential logic, ladder is beautifully clear and intuitive. But imagine you're not doing discrete manufacturing. Imagine you're running a chemical process, a reactor where you need to maintain a precise temperature by adjusting the steam flow, a distillation column where you need to control the reflux ratio based on a continuous measurement of product composition. These are analog problems, not digital ones. You're not asking, is the valve open or closed? You're asking, how far open should the valve be, right now, given that the temperature is 2 degrees above set point and rising at ½ a degree per minute? This kind of math, continuous math, is awkward in ladder logic. You can do it, but the resulting program looks cluttered and hard to read. The rungs get long and tangled with math function blocks and comparison instructions that don't really fit the contact and coil metaphor. And that brings us to the second language, structured text, usually abbreviated ST. If ladder logic was designed for electricians, structured text was designed for people who think like programmers. It looks like a conventional text-based programming language. If you've ever written code in Pascal or C or Python, structured text is going to feel familiar. You write statements. You use if-then-else constructs. You use loops. You assign values to variables using a specific syntax. In many implementations, setting a variable looks like this. You write the variable name, then a colon followed by an equals sign, then the value, then a semicolon. Green light, colon, equals true, semicolon. That's a complete structured text statement. It says, turn the green light on. Structured text shines where ladder logic struggles. Complex mathematical calculations? Easy. String manipulation? Doable. Nested conditional logic with multiple levels of if-then-else? Much cleaner in text than in graphical rungs. PID control algorithms, which we'll talk about more later? often much more readable when written as a sequence of mathematical statements rather than as a sprawl of function blocks wired together on a ladder rung. But structured text has its own limitation, and it's the mirror image of ladder logics. It's harder for electricians and maintenance technicians to read. If you don't have a programming background, looking at a page of structured text can be intimidating. It's just words and symbols and semicolons. There's no visual flow. There's nothing that maps onto the familiar world of electrical schematics. And on a factory floor, when something goes wrong at 2 in the morning and the maintenance electrician needs to figure out why the production line stopped, readability matters enormously. You want the person troubleshooting the system to be able to look at the program and quickly understand what it's supposed to be doing. So neither ladder logic nor structured text is universally better. Each is better for certain problems and certain people, and the recognition that different situations call for different modes of expression. That's exactly why the IEC standard includes 3 more languages. The third language is Function Block Diagram, abbreviated FBD. This is a graphical language, but it doesn't look like an electrical schematic the way ladder does. Instead, it looks like a signal flow diagram. You have blocks, each representing a function, an addition, a comparison, a PID controller, a timer, whatever, and you draw lines between the blocks to show how signals flow from one function to the next. If you've ever seen a block diagram in a control systems textbook, function block diagrams look a lot like that. FBD is particularly popular in process control, where you're dealing with continuous signals and feedback loops. You can see visually how the output of one calculation feeds into the input of the next. It's the language that often makes the most sense to process control engineers, people who think in terms of signal flow and transfer functions, rather than in terms of relay contacts or lines of code. The fourth language is Sequential Function Chart, or SFC, and this one is specialized for a particular kind of problem, batch processes. A batch process is one where you execute a series of steps in a specific order. Think about brewing beer, or mixing pharmaceuticals, or making paint. You add ingredient A, you heat to a certain temperature. You hold at that temperature for 30 minutes. You add ingredient B. You cool to a different temperature. You stir for an hour. Each step has to complete before the next one begins, and there might be conditions that have to be met before a transition from one step to the next is allowed. SFC represents this as, essentially, a flowchart. Steps are shown as boxes. Transitions between steps are shown as horizontal bars with conditions attached. You can see the entire sequence at a glance. You can tell, immediately, which step the process is currently in. You can see what condition needs to be met before the next step begins. For batch processes, this visual representation of the sequence is enormously powerful. It maps directly onto how operators and process engineers think about the process, as a recipe with steps. And the fifth language, which is the most specialized and least commonly encountered, is Instruction List, abbreviated IL. Instruction List is essentially assembly language for PLCs. Low-level, text-based, with commands like LD for load and OR, out for output. Each line is a single instruction. It's compact and efficient in terms of memory usage, which mattered more in the early days of PLCs when memory was expensive and scarce. Today, you're most likely to encounter Instruction List in legacy systems, older PLC programs that were written decades ago and are still running, or in applications involving motion control and robotics, where G-code, a similar kind of step-by-step instruction language, is common for controlling CNC machines and robotic arms. Now, here's what I find really fascinating about these 5 languages, and it's something that often gets lost when people talk about the IEC standard. The standard doesn't say you have to pick one and only one. In fact, it explicitly allows you to mix them. You can write one part of your program in ladder logic, another part in structured text, and yet another part in function block diagrams, all within the same PLC, all running together, all interacting. Why would you do that? Because different parts of the same machine might call for different languages. The safety interlocks, the logic that says, if the guard door is open, stop the press immediately. That's classic binary logic. Ladder is perfect for it. The PID control loop that maintains the hydraulic pressure? Maybe function block diagram makes that clearest. The recipe manager that orchestrates the batch sequence. Sequential function chart. The complex trigonometric calculation that converts encoder readings into a position in three-dimensional space. Structured text, probably, because math reads better as text. The program becomes multilingual, different parts of it speaking different languages, all translated into machine code that the PLC executes as one unified program. And this is more common than you might think. In a large pharmaceutical plant, for instance, you might have hundreds of programs running across dozens of PLCs. Some of those programs, the basic motor control and valve sequencing, are in ladder, because that's what the maintenance electricians can troubleshoot at 3 in the morning. The batch recipe management might be running as sequential function charts, because batch processes are inherently sequential, and SFC makes that sequence visible. The advanced regulatory control, the tight temperature and pressure loops, might use function block diagrams because the process engineers who tuned them think in terms of signal flow. And the data handling routines that pack production data into formatted strings for the historian database might be in structured text because string manipulation in a graphical language is painful. Nobody planned this multilingual situation. It emerged organically over years as different engineers with different backgrounds worked on different parts of the system. And it works. Not always elegantly, but functionally. Because each part of the system is expressed in the language that best fits the people who need to understand and maintain it. And the people writing different parts of the program might literally be different people, with different backgrounds and different ways of thinking. The electrician writes the interlocks in ladder. The process engineer writes the control loops in FBD. The software-inclined controls engineer writes the math in structured text. Each person working in the language that fits their mind. And this, I think, is one of the most underappreciated aspects of how we communicate with machines. There is no single best language. There are only languages that fit particular minds and particular problems more or less well. And the history of programming languages, not just for PLCs but for all computing, is really a history of people trying to find better and better fits between the way humans think and the way machines need to be instructed. But the languages we've been talking about so far, or 5 of them, share a common limitation. They all tell the machine what to do. They're all about giving instructions. Open this valve, start this motor, calculate this value, follow this sequence. They're conversations that flow in one direction, from human to machine. And that's fine for many applications. But as automated systems grew more complex, as they started managing entire factories and power plants and water treatment facilities, a new problem emerged. The machines needed to talk back. The humans operating these systems needed to see what the machine was doing, needed to understand the state of the process, needed to be alerted when something went wrong. The conversation needed to become two-way. And the devices and systems that made that two-way conversation possible, the screens and panels and dashboards that gave machines a face and a voice, those are what we need to talk about next. Because the way information flows back from machine to human turns out to be just as important and just as tricky as the way instructions flow from human to machine. Let's think about what it's like to be an operator in a factory. Not a controls engineer who writes programs and designs systems. An operator. The person who actually runs the machine, day after day, shift after shift. You're standing in front of a process. Maybe it's a water treatment plant, Maybe it's a food processing line. Maybe it's a chemical reactor. And the process has dozens of variables that matter. Temperatures, pressures, flow rates, levels, speeds, concentrations. Some of these variables are changing slowly, over minutes or hours. Some can change in seconds. And you need to know, at any given moment, what's happening. You need to know whether things are running normally or whether something is drifting toward a dangerous condition. And when something does go wrong, you need to know what it is, where it is, and how serious it is. And you need to know all of that quickly. Because in some processes, the difference between catching a problem in 30 seconds and catching it in 5 minutes is the difference between a minor adjustment and a catastrophic failure. In the old days, before computers, this information came to you through physical instruments. Gauges with needles, thermometers mounted on pipes, pressure indicators with colored bands showing the safe range. Indicator lights, red for alarm, green for normal. Annunciator panels with rows of backlit windows, each one labeled with a different alarm condition. When something went wrong, the corresponding window would flash and a horn would sound, and you'd look at the panel and see, okay, high temperature, reactor 3, and you'd go deal with it. These physical panels worked, but they had the same scaling problem as relay panels. As processes got more complex, the panels got bigger. More gauges, more lights, more buttons. Control rooms started to look like the cockpit of a space shuttle, every surface covered with instruments. And the problem wasn't just the physical space. The problem was cognitive. There was simply too much information for a human being to monitor effectively. Studies showed that operators in large control rooms would regularly miss important alarms because they were drowned out by the sheer volume of less important ones. Alarm fatigue, they called it. When everything is beeping, nothing is beeping. The solution, or at least the first step toward a solution, came from the same digital revolution that had given us the PLC. If the PLC could replace a room full of relays with a single box, maybe a computer screen could replace a wall full of gauges with a single display. And that idea, the idea of replacing physical instruments with computer graphics, gave birth to what the industry calls the HMI, the Human-Machine Interface. An HMI, at its simplest, is a screen that shows you what the machine is doing. It's the machine's face, the window through which it communicates its status to you. And if you've ever seen pictures of a modern factory control room, you've seen HMIs. They're the flat panel displays showing colorful graphics of pipes and tanks and pumps, with numbers floating next to each component showing the current temperature, the current flow rate, the current valve position. Now, the term HMI is specific to the industrial world. If you have a software engineering background, you might recognize a related concept, the GUI, the graphical user interface. An HMI is essentially a GUI for a machine, but there's an important difference in emphasis. A GUI on your computer or phone is designed primarily for you to give commands to the software. Click this button, drag this slider, type in this field. The flow of information is mostly from human to computer. An HMI in a factory is designed primarily for the machine to communicate its status to the human. The flow is mostly from machine to human. Yes, you can also use the HMI to give commands, start a motor, change a set point, acknowledge an alarm. But the primary job of the HMI is to make the invisible visible, to take the abstract world of voltages and signals flowing through the PLC and turn it into something a human can see and understand at a glance. And designing a good HMI is harder than you might think, much harder. Because you're not just putting numbers on a screen, you're designing a language, a visual language that has to convey complex, dynamic information clearly and quickly to someone who might be tired, who might be dealing with a stressful situation, who might have to make a critical decision in seconds. And here's a fascinating thing about HMI design that connects to a much broader question about human-machine communication. The earliest HMIs, from the 1980s and 90s, tended to look like the physical panels they were replacing. Engineers would draw a graphic that looked like the piping and instrumentation diagram of the process, with little animated valves and pumps, and put numbers next to everything. These displays were colorful, very colorful, bright greens and reds and blues and yellows on a black background. They looked impressive in a demo, but in practice, when an operator had to stare at these screens for 12 hours on a shift, the visual clutter was overwhelming. Everything was bright, nothing stood out. When an alarm condition occurred, the operator had to scan across a kaleidoscope of color and animation to find the one thing that was different. The evolution of HMI design philosophy over the past 3 decades is really a story about learning to respect the limitations of human attention, and the lessons, paid for in accidents and near misses, have reshaped the entire field. Bad HMI design can kill people. That's not an exaggeration. When the 3 Mile Island nuclear accident happened in 1979, one of the contributing factors was the control room design. The operators were getting ambiguous, confusing information from their instruments. An indicator light told them a valve had been commanded to close, but it didn't tell them whether the valve had actually closed. It hadn't. And because the operators couldn't see the true state of the system through their instruments, they made decisions that made the situation worse rather than better. Good HMI design follows principles that have been developed over decades of hard experience. Keep it simple. Don't clutter the screen with information the operator doesn't need right now. Use color sparingly and consistently so that when something turns red, it means the same thing everywhere. Make the most important information the most visually prominent. Group related information together. Make navigation intuitive so the operator can drill down from an overview to a detail view quickly. Some of the best HMI design work follows what's called a high-performance philosophy, developed by people like Bill Holyfield and Eddie Habibi. The idea is that the normal state of the display should be mostly gray, subdued, calm. When everything is running normally, the screen should be boring, and when something goes wrong, the abnormal condition should leap out visually, a splash of color in a sea of gray. This way, the operator's eye is drawn immediately to the thing that needs attention. The machine is saying, in visual language, "Hey, look over here. This is the thing that matters right now." Now, when you scale this up, when you go from a single HMI managing one piece of equipment to a system that oversees an entire plant, an entire facility, you enter the realm of what's called SCADA, which stands for Supervisory Control and Data Acquisition. A SCADA system is, in essence, an HMI on steroids. It doesn't just display the status of one machine, it pulls data from dozens or hundreds of PLCs and sensors across the entire facility, aggregates that data, displays it on multiple screens in a control room, logs it to databases for later analysis, generates alarms when things go out of spec, and allows operators to send commands to any part of the process from a central location. A large refinery might have a SCADA system monitoring tens of thousands of data points. Temperatures, pressures, flows, valve positions, motor statuses, tank levels, all streaming in continuously, all being logged, all being checked against alarm limits, all being displayed on operator screens in real time. The SCADA system is the nervous system of the plant. It's how the plant talks to the people who run it. And here's something that connects this directly to the language theme we've been following. The SCADA system doesn't just display raw numbers, it interprets them. It translates the raw data into context that a human can act on. A temperature reading of 412 degrees Fahrenheit means nothing on its own. But a temperature reading of 412 degrees Fahrenheit, shown in red, next to the label reactor outlet, with a high alarm limit of 415, with a trend graph showing the temperature rising steadily over the last 20 minutes, that tells a story. It says, "This reactor is getting hotter. It's approaching the limit, and it's been doing so consistently, not just a momentary spike." The SCADA system has translated raw data into narrative. It's telling the operator not just what the number is, but what it means and what's likely to happen next if nothing changes. And at this point, we've been talking about language flowing in two directions, from human to machine through ladder logic, structured text, and the other programming languages, and from machine to human through HMIs and SCADA displays and alarm systems. But there's a third flow of language that's often overlooked, and it's arguably the most critical of all. It's the language that machines use to talk to each other. Because in a modern automated facility, the PLC running the reactor isn't the only intelligent device. There's a PLC for the reactor, another PLC for the distillation column, another for the tank farm, another for the utilities, another for the packaging line. And these PLCs need to communicate. The reactor PLC needs to tell the distillation column PLC that a batch is ready. The tank farm PLC needs to tell the packaging PLC which tank to draw from. The utilities PLC needs to know the demand from all the other systems so it can adjust the steam and power generation. And below the PLCs, at the field level, there are smart devices, variable frequency drives that control motor speed, smart transmitters that measure temperature and pressure and flow, networked valve positioners. All of these devices communicate using industrial protocols, specialized languages designed for machines to talk to each other reliably and quickly. Protocols like Ethernet/IP, Profinet, Modbus TCP/IP, EtherCAT. Each one a different dialect, optimized for different requirements of speed, determinism, and interoperability. This web of communication, human to machine, machine to human, machine to machine, all layered on top of each other, is sometimes visualized as a pyramid, the automation pyramid. And understanding this pyramid, understanding how all these layers of language stack up, is essential for understanding how modern automated systems actually work. The pyramid has been a cornerstone concept in the field for decades, and it's worth spending some time with because it reveals the hidden architecture beneath the surface of every automated facility you've ever driven past on the highway. The automation pyramid. It's one of those concepts that sounds like textbook jargon until you actually see what it describes, and then you realize it's just a really clear way of mapping out how all the pieces of an automated system fit together. Each layer of the pyramid speaks a different language, operates at a different speed, and serves a different purpose. And the way these layers interact tells you a lot about the fundamental challenges of making machines work together. At the bottom of the pyramid, at the very base, is the field level. This is where the physical world meets the electrical world. This is where you find the sensors that measure things: temperature sensors, pressure sensors, flow meters, level detectors, proximity switches, and the actuators that do things: motors, valves, solenoid-operated cylinders, heaters, conveyors. These devices are the hands and eyes of the system. They're the interface between the abstract world of control logic and the concrete world of liquids and metals and temperatures and pressures. At the field level, the language is the simplest and most direct. A temperature sensor sends a signal, typically an analog current between 4 and 20 milliamps, that's proportional to the temperature. A proximity switch sends a digital signal, either 24 volts or 0 volts, meaning something is here, or nothing is here. A motor contactor either closes or opens, running the motor or stopping it. The vocabulary at this level is tiny: on, off. A number between 0 and 100%. The grammar is just electrical physics. And the physical infrastructure that supports this language is worth noticing, because you encounter it in every industrial control panel, everywhere in the world. The components are mounted on standardized metal rails called DIN rail, a specific profile of bent metal that provides a universal mounting system. Everything clips onto DIN rail: PLCs, power supplies, terminal blocks, relays, circuit breakers. If you've ever looked inside an industrial control cabinet, you've seen row after row of components, all clipped to these metal rails, all wired together through terminal blocks. Terminal blocks are the meeting places of wires. Think of them as standardized connection points, where a wire coming from a sensor in the field can meet the wire going to an input on the PLC. They come in different types. Plain ones for general connections, green ones for grounding, fused ones that include built-in overcurrent protection, multi-level ones that pack 2 or 3 separate circuits into the footprint of one block for when space is tight. They're simple devices, but they're everywhere, and they're critical for keeping a panel organized and maintainable. When you can trace a wire from the field to a specific terminal block, and from that terminal block to a specific input on the PLC, troubleshooting becomes systematic rather than chaotic. And then there's the power supply. Every control panel needs one. It takes the AC power coming in from the building or the plant, typically 120 or 240 volts, and converts it to the DC voltage that most modern control components use, typically 24 volts. Why 24 volts DC? Because low voltage is safer, much safer. Working with 24 volts DC, you're not going to get a dangerous shock. Working with 480 volts AC, which is what powers the large motors in a plant, you absolutely can. And in a world where technicians are regularly opening control panels, pulling wires and probing circuits, safety matters enormously. Between the field level and the control level, you often find relays. A relay, as we discussed earlier, is an electrically operated switch. In modern systems, relays serve a more specialized role than they did in the pre-PLC era. They're used primarily for signal conversion, to bridge between circuits at different voltage levels, and for safety circuits that need to be independent of the PLC, because even PLCs can fail, and certain safety functions need to operate no matter what. Moving up the pyramid, the next layer is the control level. This is where the PLCs live. This is the brain of the operation. The PLC reads the signals from all the field devices, executes its program, the ladder logic or structured text, or whatever combination of languages the programmer used, and sends commands back out to the field devices. All of this happens in a cycle. The PLC reads all inputs, executes the program from top to bottom, and updates all outputs. Then it does it again, and again, and again. This cycle time, the time it takes to complete one full pass through the program, is typically measured in milliseconds. 10 milliseconds, 20, maybe 50 for a large, complex program. Multiple times per second, the PLC is scanning the state of the entire system and updating its outputs accordingly. And between the field level and the control level, there's a physical reality that's easy to overlook when you're thinking about languages and algorithms, but that every practicing controls engineer knows intimately. That reality is wiring. Thousands of wires connecting thousands of field devices to the PLC inputs and outputs, running through cable trays and conduit, terminated at terminal blocks inside control panels. Getting the wiring right is absolutely fundamental. A temperature sensor wired to the wrong input channel means the PLC is reading the wrong temperature. A motor wired to the wrong output means the wrong motor starts when you press the button. And tracing a wiring error through a panel with hundreds of terminations can take hours. This is why electrical schematics matter so much in the controls world. A good set of schematics is a map of the physical language of the system. Every wire documented, every termination numbered, every device labeled. When something goes wrong at 2 in the morning and a maintenance technician is standing in front of a panel with a flashlight and a multimeter, those schematics are the difference between fixing the problem in 20 minutes and being there until dawn. Also at the control level, you find the network infrastructure. Ethernet switches that connect PLCs to each other and to the supervisory level above. These aren't the same consumer-grade switches you'd buy for your home network, though they look similar. Industrial Ethernet switches are built to withstand temperature extremes, vibration, electrical noise, all the things that a factory environment throws at them. They're the postal service of the control level, carrying messages between devices reliably and on time. Above the control level sits the supervisory level. This is where the SCADA systems and HMIs live. This is where operators sit in the control room, watching their screens, monitoring trends, acknowledging alarms, and occasionally sending commands down to the PLCs. The language at this level is richer and more nuanced than at the levels below. It includes not just current values, but historical trends, not just raw data, but contextualized information. Not just what's happening now, but what happened over the last shift, the last day, the last month. Data logging is particularly important. Modern plants use specialized software called historians, databases optimized for storing time series data, millions of data points per day, tagged with timestamps and quality codes, compressed and stored for years. If a quality problem shows up in a batch of product 3 months from now, the historian allows you to go back and look at exactly what every temperature, every pressure, every flow rate was doing during the production of that batch. It's the plant's memory. And the language of querying that memory, SQL or proprietary historian query languages, is yet another dialect in the multilingual world of automation. Trend analysis, alarm management, reporting, all happen at this level. And above the supervisory level, in some facilities, there's an enterprise level. This is where the automation system meets the business system, the MES, the manufacturing execution system, which tracks production, manages work orders, and coordinates scheduling. The ERP, the Enterprise Resource Planning System, things like SAP, which manages the business side, inventory, purchasing, sales, finance. When the SCADA system reports that a batch of product has been completed, that information can flow up to the MES, which can update the production count, trigger the next work order, and report the results to the ERP, which can update the inventory and generate a shipping order. Now, not every facility has all these layers. A small machine shop might have a PLC and a simple HMI and nothing above that. A large oil refinery or pharmaceutical plant might have the full stack, from field sensors all the way up to an ERP system, with data flowing continuously up and down through every layer. But the pyramid structure, the idea that you can organize an automated system into layers of increasing abstraction, from raw electrical signals at the bottom to business decisions at the top, that framework holds everywhere. And each layer of the pyramid speaks a different language. At the field level, it's voltages and currents. At the control level, it's PLC programs in ladder logic and structured text. At the supervisory level, it's graphical displays and alarm messages. At the enterprise level, it's database queries and API calls and JSON and XML. Each layer translates the language below it into something more abstract, more contextualized, more useful for the decisions that need to be made at that level. In a sense, the entire automation pyramid is a translation machine. It takes the raw, low-level language of the physical world, the voltage on a thermocouple, the state of a limit switch, and translates it upward through progressively higher levels of abstraction until it becomes something a plant manager can read in a report. And it takes the high-level language of business decisions. We need to produce 10,000 units of product X by Friday, and translates it downward through progressively lower levels until it becomes specific commands to specific motors and valves. The elegance of this system is real, and it works remarkably well when everything is set up correctly. But there's a whole different kind of language running in parallel to all of this. A language that isn't about wiring or programming or displaying data, but about understanding the fundamental behavior of the systems you're trying to control. A mathematical language. And it turns out that this mathematical language, developed by physicists and engineers starting in the 19th century and continuing through the 20th, is what makes sophisticated control possible. Without it, all the PLCs and HMIs and SCADA systems in the world would be limited to simple on-off logic and manual adjustment. With it, machines can do things that seem almost intelligent, maintaining precise temperatures, following complex trajectories, adapting to changing conditions, predicting the future. This mathematical language has its own grammar, its own vocabulary, its own way of describing the world. And the story of how it was developed is one of the most fascinating in all of engineering. It began, of all places, with a problem about steam engines. So we've been talking about the languages that humans use to give instructions to machines. Ladder logic, structured text, function block diagrams, the visual languages of HMIs and SCADA displays. All of these are what you might call operational languages. They tell the machine what to do in specific situations. If this, then that. When the temperature exceeds 400 degrees, close the valve. When the level drops below 30%, start the pump. But there's another layer of language that lies beneath all of this, a language that doesn't describe what to do, but describes how the system behaves, how a tank fills when you open a valve, how a motor accelerates when you apply voltage, how a temperature changes when you increase the heat, how the output of any system responds to a change in its input. This is the language of mathematics. And while it might seem like we're leaving the practical world of PLCs and factories behind, we're really not. Because every sophisticated control strategy running in every PLC in the world, every PID loop, every model predictive controller, every feed-forward algorithm, is based on this mathematical language. The PLC doesn't know the math. It just executes the instructions that the math produced. But somebody had to do the math first. Somebody had to understand the system deeply enough to write those instructions. And the language they use to achieve that understanding is what we're going to explore now. Let's start with a question that seems almost too simple to be useful. If you open a valve and let water flow into a tank, what happens? The level rises, obviously. But how fast does it rise? And does the rate of rise stay constant, or does it change over time? And if there's water flowing out of the tank through a drain at the bottom, does the level reach a steady state? And if so, what determines that steady state? These are the kinds of questions that a discipline called system dynamics is concerned with. And the language it uses to answer them is the language of differential equations. A differential equation is simply a mathematical statement about how something changes over time. The rate at which the tank level changes equals the inflow rate minus the outflow rate. That's a differential equation. It tells you the relationship between the current state of the system, the water level, and how that state is changing, the rate of rise or fall. Now, for a simple tank, you can probably solve this in your head. But real industrial processes aren't simple tanks. They're networks of tanks and pipes and heat exchangers and reactors and separators, all interacting with each other. The differential equations get complex fast, and solving them by hand becomes impractical or impossible. This is where engineers in the early 20th century developed a powerful trick. Instead of trying to solve the differential equations directly in the time domain, which asks, what happens moment by moment, they transformed the equations into a different mathematical space, where the algebra was much easier. The tool for this transformation was developed by a French mathematician named Pierre-Simon Laplace in the late 18th century, and it's called, naturally enough, the Laplace transform. Without getting into the mathematical details, which is perfectly fine for tonight, here's what the Laplace transform does. It takes a differential equation, which is hard to solve because it involves rates of change, and converts it into an algebraic equation, which is much easier because it's just multiplication and division. You solve the easy algebraic equation, and then you transform the answer back to get the time domain solution. It's like using a foreign dictionary. You have a sentence in a language you can't pass, the differential equation. You translate each word into a language you're more comfortable with, the Laplace domain, figure out the meaning, and then translate the answer back. And in the Laplace domain, something beautiful happens. The entire behavior of a system, how it responds to any input, can be captured in a single mathematical object called a transfer function. The transfer function is, in essence, the system's personality, condensed into a compact mathematical expression. If you know the transfer function, you know everything about how the system behaves. You can predict its response to any input. You can tell whether it will be stable or unstable. You can calculate how fast it will respond, how much it will overshoot, whether it will oscillate. Think about what the transfer function really is. It's a compressed description, a summary, a way of capturing in a single mathematical expression everything you need to know about how a system responds. If the transfer function of your system is a certain expression involving the Laplace variable s, then you can predict what happens when you give the system a step input, a sudden change. You can predict what happens when you give it a sinusoidal input at any frequency. You can tell whether it oscillates. You can tell how fast it responds. You can tell how much overshoot it produces. All from this one expression. And transfer functions became the lingua franca of control engineering in the mid-20th century. An engineer at Bell Labs working on telephone amplifiers, and an engineer at an auto plant working on a speed controller, and an engineer at NASA working on a rocket guidance system could all describe their systems using transfer functions, and they'd immediately understand each other. Different physical systems, same mathematical language. And this mathematical language came with its own set of tools for visualization and analysis. Tools with names that every engineering student learns and that every practicing control engineer uses. Bode plots, named after Hendrik Bode, which show how a system's gain and phase shift vary with frequency. Nyquist plots, named after Harry Nyquist, which map the frequency response onto a single curve in the complex plane and let you determine stability with a visual test. Root locus plots, developed by Walter Evans in the late 1940s, which show how the characteristic roots of a system move as you change a design parameter. Each of these tools is a different way of looking at the same underlying information, the transfer function, from a different angle. Just as a sculptor might walk around a statue, viewing it from the front, the side, the top, each view revealing something the others don't, an engineer examines a transfer function through multiple graphical tools, each one illuminating a different aspect of the system's behavior. And here's what ties all of this back to the language theme we've been following. These mathematical tools aren't just abstract theory. They're the language in which control system design is conducted. When an engineer sits down to design a controller for a new process, they start by identifying the transfer function of the process, either from first principles, the physics equations, or from experimental data. Poke the system, measure the response, fit a model. Then they draw the Bode plot or the root locus. Then they design a controller that shapes the frequency response or moves the roots to where they want them. And then, and only then, do they translate that controller into the operational language of the PLC, into ladder logic, or structured text, or function block diagrams. The mathematical language is the design language. The PLC language is the implementation language. And the gap between design and implementation, the act of translating a carefully designed controller from mathematical notation into PLC code, is one of the places where things can go wrong. A controller that looks perfect on a Bode plot can behave badly in a PLC if the programmer makes a numerical error or uses an inappropriate sampling rate or doesn't handle the boundary conditions correctly. The translation between languages is always a potential source of error. Think about it this way. A control engineer designs a controller using MATLAB or a similar tool on their laptop. The mathematics is continuous. The time is a smooth, flowing variable. But when that controller gets implemented on a PLC, time becomes discrete. The PLC scans its program in cycles, maybe every 10 or 20 milliseconds. Between scans, the PLC doesn't know what's happening. It's blind. And if the process dynamics are fast relative to the scan time, if things change significantly between one scan and the next, the controller's behavior can diverge from what the continuous time design predicted. This is the sampling problem, and it's one of the fundamental challenges of digital control. The mathematical language of continuous time control theory and the operational language of discrete time PLC execution don't map onto each other perfectly. There's always a translation gap, and managing that gap, choosing the right scan rate, implementing the right discretization method, handling the numerical precision limits of the PLC's processor, is a critical skill that lives at the boundary between control theory and PLC programming. It's yet another reminder that having the right language for the design and the right language for the implementation doesn't mean the translation between them is trivial. Every translation between any two languages risks losing something in the process. The art is in minimizing that loss. But within this mathematical language, there's one particular sentence that deserves special attention. Because this sentence, this three-part mathematical expression, turns out to be so universally useful, so robust, so adaptable, that it handles the vast majority of all control problems in the world. It's called PID, Proportional Integral Derivative. And its story is worth telling carefully, because it illustrates something profound about the relationship between simplicity and power in any language. PID. 3 letters, 3 concepts, 3 terms added together, and between them, they handle roughly 90% of all industrial control loops on the planet. The thermostat in the building you're in right now, probably running a version of PID. The cruise control in your car, PID. The temperature controller in a pharmaceutical reactor, PID. The level controller on a water treatment clarifier, PID. The pressure controller on a natural gas pipeline, PID. It's everywhere. It is, without exaggeration, the most successful and widely deployed control algorithm in the history of engineering. And the beautiful thing is, the idea behind it is genuinely intuitive. You don't need advanced math to understand why PID works. You just need to think about what it means to correct an error. Imagine you're driving a car on a long, straight highway, and you want to hold a speed of exactly 60 miles per hour. You look at the speedometer, and you see you're going 55. You've got an error. You're 5 miles per hour below your target. What do? The proportional response is the most obvious one. You're below speed, so you press the gas pedal harder. And the amount you press it depends on how far off you are. If you're only 1 mile per hour below target, you press a little. If you're 10 below, you press a lot. The correction is proportional to the error. Bigger error, bigger response. Smaller error, smaller response. This works pretty well, but it has a flaw. Imagine you're driving up a gentle hill. The hill creates a constant drag on the car. With proportional control alone, you'd settle into a speed that's a little below your target, maybe 58 instead of 60. You'd press the gas harder because of the 2 mile per hour error, and that extra gas would partially compensate for the hill, but not completely. You'd need a specific amount of extra gas to fully overcome the hill, and the proportional controller alone doesn't know that. It just responds to the current error. And the current error, that 2 miles per hour, is what's needed to generate the correction that partially overcomes the hill. If the error went to 0, the correction would go to 0 too, and you'd immediately start slowing down again. This persistent offset is a fundamental limitation of pure proportional control. And the fix is the integral term. The integral term looks at the accumulated error over time. If you've been 2 miles per hour below target for 30 seconds, the integral term notices that this error has been hanging around, and it adds a little more correction. The longer the error persists, the more the integral term pushes. Eventually, it pushes hard enough to eliminate the offset entirely. The integral term is, in a sense, the system's patience running out. It's saying, "I've been off by 2 miles per hour for long enough, let me push a little harder." But the integral term introduces its own problem. Because it accumulates, it builds momentum. If you're approaching your target speed quickly, the integral term has been building up ahead of steam, and it can push you past the target. You overshoot. Then you're too fast, the error reverses, and the integral term starts accumulating in the other direction. You overshoot below. And you can get into an oscillation, swinging above and below the target, slowly settling down, or, in bad cases, not settling at all. And that's where the derivative term comes in. The derivative term looks at the rate of change of the error, not where the error is, but where it's going. If the error is shrinking rapidly, meaning you're approaching the target fast, the derivative term says, "Ease off, you're about to arrive, don't overshoot." If the error is growing rapidly, meaning things are getting worse fast, the derivative says, "Push harder, we're moving in the wrong direction and accelerating." The derivative term is the anticipatory part. It's the difference between a driver who only looks at the speedometer and a driver who also feels the car accelerating or decelerating. That sense of rate, that feel for the trend, is what smooths out the response and prevents the oscillation that the integral term can cause. 3 terms. Proportional corrects based on the current error. Integral corrects based on the accumulated past. Derivative corrects based on the predicted near future. Together, they form a remarkably effective controller that handles a huge range of situations. Now, in the mathematical language we were talking about, the PID controller has a specific transfer function, and in the PLC implementation language, it's typically available as a pre-built function block. You drag the PID block into your program, whether it's in ladder logic or function block diagram or structured text. You connect the process variable, the measurement, to one input and the set point, the target, to another. And you configure 3 numbers, the 3 tuning parameters, the proportional gain, the integral time, and the derivative time. These 3 numbers determine the personality of the controller, how aggressively it reacts, how quickly it eliminates offset, how much it anticipates. And finding the right values for those 3 numbers, the act of tuning the controller, is both an art and a science. In 1942, 2 engineers named John Ziegler and Nathaniel Nichols published a set of tuning rules that are still used today. Their method was pragmatic. You experimentally determine how the process responds to a small change, and from that response, you calculate starting values for the 3 PID parameters. The Ziegler-Nichols method doesn't give you optimal tuning, but it gives you a reasonable starting point. And from there, you can adjust by observation and experience. Now, the art of tuning, of finding the right balance between these 3 terms, is one of those things that experienced control engineers develop a feel for over time. Push the proportional gain too high, and the system becomes jittery, reacting too aggressively to every small disturbance. Push the integral time too short, and the system overshoots and oscillates as the integral term accumulates too quickly. Push the derivative too high, and the system becomes hypersensitive to noise in the measurement signal, because noise creates rapid changes in the error signal, and the derivative term amplifies those rapid changes. Every new controls engineer goes through the experience of sitting in front of a system, adjusting the PID parameters, watching the response on a trend chart, adjusting again, watching again. You develop an intuition. You learn to read the shape of the response curve. A slow, sluggish approach to set point with no overshoot tells you the proportional gain is too low. A sharp overshoot followed by damped oscillation tells you the integral is too aggressive. A ragged, noisy output signal tells you the derivative is amplifying measurement noise. And despite all the advanced control techniques that have been developed since, this ritual, the act of watching a trend and adjusting PID parameters, is still happening right now in factories and plants all over the world. It's the most hands-on, most tangible form of talking to a machine that exists in the controls profession. You tweak a number. You watch what the machine does. You tweak again. You and the machine are having a conversation, finding a common language through iteration. There's something deeply satisfying about PID control once you understand it. It's a tiny program, a few lines of code, and yet it contains within it three fundamentally different strategies for dealing with error. React to what's happening now. Learn from what's happened before. Anticipate what's about to happen. And the fact that this combination works so well in so many different contexts, from chemical reactors to cruise missiles to the temperature of the coffee in your office's brew station, tells you something about the universality of these three ideas. They're not specific to any particular engineering domain. They're about the nature of error correction itself. But PID has its limits. And those limits became increasingly apparent as the systems being controlled grew more complex. A PID controller controls one thing, one temperature, one pressure, one speed, one variable at a time. And it does so by looking at one error signal and calculating one output, one input, one output. The formal term is SISO, single input, single output. But real systems are almost never truly SISO. Think about an airplane. You've got ailerons affecting roll, but also creating unwanted yaw. You've got elevators affecting pitch, but also changing speed. Every control surface affects multiple variables, and every variable is affected by multiple control surfaces. You can't just design 5 independent PID loops for 5 variables and expect them to work harmoniously. They'll fight each other. Controller A adjusts something that Controller B was relying on being constant, which causes Controller B to react, which changes something that Controller A depends on, and you get an unstable mess. Handling these interconnected, multi-variable systems requires a different mathematical framework entirely. A framework where you don't describe the system as a single transfer function mapping one input to one output, but as a matrix of transfer functions, capturing all the interactions between all the inputs and all the outputs simultaneously. And the person who crystallized this framework, who turned it into something engineers could actually use, approached it with a completely different philosophy from the transfer function and Bode plot tradition. He said, instead of describing what the system does from the outside, let's describe what the system is on the inside. Instead of looking at the input-output relationship, let's look at the internal state. And that shift, from describing behavior to describing being, from input-output to state space, was one of the most important conceptual transitions in the entire history of control engineering. The man who catalyzed this shift was named Rudolf Kálmán, and the framework he built is called state-space control theory. Sometimes it's called modern control theory to distinguish it from the classical theory of Bode and Nyquist and transfer functions. Although by now, Kálmán's work is over 60 years old, so calling it modern feels a bit optimistic. But the core idea is powerful and worth sitting with for a moment. Because it represents a fundamentally different way of describing a system, a fundamentally different language. In the classical approach, you describe a system by what it does. You hit it with an input and measure the output. The relationship between them is the transfer function. It's like describing a person by what they say when you ask them questions. You don't know what's going on inside their head. You just know the input, your question, and the output, their answer. In the state space approach, you describe a system by what it is. You identify the internal variables, the state variables, that completely characterize the system's condition at any moment. And you write equations that describe how those state variables change over time in response to inputs. Here's a concrete example. Imagine a simple cart on a track, the kind of thing you might see in a physics demonstration. You push it, and it rolls. In the classical approach, you'd describe the system by its transfer function, the relationship between the force you apply, the input, and the position of the cart, the output. One equation, input to output, black box. You don't care what's inside. In the state space approach, you'd identify the state variables, the position of the cart and the velocity of the cart, two variables. And you'd write two equations, one describing how the position changes, it changes at a rate equal to the velocity, and one describing how the velocity changes, it changes at a rate proportional to the applied force divided by the mass. Two equations, two state variables, capturing the entire dynamics of the system. Here's an analogy that might help. The transfer function approach is like knowing a person only through their email. You send them a message, they send a reply. You learn their response pattern. You can predict what they'll say to different kinds of messages. But you don't know anything about what's going on inside their head. You don't know their mood, their motivations, their internal state. The state space approach is like actually understanding what the person is thinking and feeling. You know their internal state, and from that, you can predict not just their response to your next email, but their response to any situation, including situations you've never put them in before. Now for this simple cart, the two approaches give you the same information in different clothing. You can convert one to the other and back. But as systems get more complex, as you add more components, more interactions, more variables, the state space approach scales much more gracefully. A system with 10 interacting variables has a 10-dimensional state vector, and the dynamics are captured by a 10 by 10 matrix. That's compact. That's tractable. Try to write out all the cross-coupling transfer functions for a 10-variable system in the classical approach, and you drown in a sea of individual transfer functions. Kalman formalized this in a notation that's become universal. The state of the system is represented by a vector, usually called x. The rate of change of the state is determined by a matrix, called A, multiplied by the current state, plus another matrix, called B, multiplied by the control input. And the output you can observe is another matrix, called C, multiplied by the state. Three matrices, A, B, and C. The A matrix captures the system's natural dynamics, how it evolves on its own. The B matrix captures how the control input affects the state. The C matrix captures what you can actually measure. This is a language, a mathematical language, and like any language, it lets you ask questions that would be difficult or impossible to formulate otherwise. Kalman asked two questions that turned out to be profoundly important. First, given the A and B matrices, given the system's dynamics and the available control inputs, can you actually steer the system from any initial state to any desired final state? In plain English, do you have enough control to get the system where you want it? Kalman called this controllability, and he showed that you could answer it definitively by performing a specific calculation on the A and B matrices. If the result has a certain mathematical property, full rank if you're curious, the system is controllable. If not, there are states you simply cannot reach with the available controls. No amount of clever programming will help. Second, given the A and C matrices, given the system's dynamics and the available measurements, can you figure out what the internal state of the system is just by watching the outputs? Can you reconstruct the hidden internal variables from the visible external measurements? Kalman called this observability. And again, a specific calculation on the A and C matrices gives you a definitive answer. If the system is observable, you can build a mathematical model called an observer that runs alongside the real system and estimates the internal state based on the measurements. If the system is not observable, some internal variables are permanently hidden from you. You can't see them, you can't estimate them, and you have to accept that limitation. These two concepts, controllability and observability, are dual to each other. They're two sides of the same coin, and they're tremendously practical. Before you start designing a controller for a complex system, you should check whether the system is controllable with the actuators you have. Before you start designing an observer to estimate the internal state, you should check whether the system is observable with the sensors you have. If either answer is no, you need more actuators or more sensors. No amount of algorithm sophistication can compensate for a fundamental lack of controllability or observability. But Kálmán's most famous contribution, the one that has arguably had the single greatest practical impact of any result in all of control theory, is something that combines both estimation and control into one elegant package. It's called the Kalman filter, and its story takes us from the abstract world of matrices and state vectors to the very concrete world of the Apollo spacecraft navigating to the moon. The Kalman filter solves a problem that seems simple to state, but is incredibly hard to solve well. The problem is this: you have a system, and you want to know its current state. Where is it? How fast is it moving? What's the temperature? What's the pressure? But your measurements are noisy. They're imperfect. Every sensor has some degree of inaccuracy, some amount of random error, and sometimes you can't even measure the variables you care about directly. You can only measure things that are related to them indirectly. So, how do you get the best possible estimate of the true state, given noisy, incomplete measurements? Before Kalman, the standard approach to this problem was developed by Norbert Wiener during World War II. Wiener's optimal filter, sometimes called the Wiener filter, was mathematically elegant, but practically difficult. It required you to know the entire statistical history of the signal and the noise. It produced a fixed filter, one that didn't change over time, and it worked in the frequency domain, which meant it was deeply connected to the Bode and Nyquist framework, but didn't fit naturally with the state-space approach. Kálmán's solution, published in 1960, was radically different in its philosophy. Instead of producing a fixed filter, Kálmán's algorithm was recursive. It updated its estimate one step at a time, incorporating each new measurement as it arrived. And instead of working in the frequency domain, it worked directly with the state-space model, the ABC matrices we just discussed. Here's the intuition behind how the Kalman filter works. Imagine you have a model of your system. You know, approximately, how the state evolves over time. So at any moment, you can predict what the state should be at the next moment, based on your model and the current control inputs. That's your prediction. Then a measurement comes in. It's noisy, but it tells you something about where the state actually is. Now you have two pieces of information: your prediction, based on the model, and your measurement, based on the sensor. And they probably don't agree perfectly because the model isn't perfect and the sensor isn't perfect. The Kalman filter blends these two pieces of information in an optimal way. If your model is very good and your sensor is very noisy, the filter trusts the model more and the measurement less. If your model is uncertain but your sensor is precise, the filter trusts the measurement more and the model less. It automatically adjusts the balance based on the relative uncertainties, which are tracked by a mathematical object called the covariance matrix. The covariance matrix is, in essence, the filter's quantified self-doubt. It knows how uncertain it is about each component of the state, and it uses that knowledge to decide how much to trust each new piece of information. And here's the detail that makes the Kalman filter feel almost alive. Between measurements, the covariance grows, the uncertainty expands. The filter is saying, I haven't seen new data in a while, and my model isn't perfect, so I'm becoming less sure of my estimate. Then a measurement comes in, and the covariance shrinks. The uncertainty contracts. The filter incorporates the new information and becomes more confident. Then the interval between measurements begins again, and the covariance starts growing again. This breathing rhythm, This expansion and contraction of uncertainty is one of the most elegant features of the algorithm. The filter knows what it doesn't know. It quantifies its own ignorance, and it uses that quantification to make the best possible use of every piece of information it receives. Now, in 1960, the Kalman filter was a theoretical result, a beautiful piece of mathematics published in a journal paper. But within a few years, it became one of the most critical pieces of technology in the American space program. Because the Apollo spacecraft had exactly the problem the Kalman filter was designed to solve. The spacecraft carried an inertial measurement unit, a set of gyroscopes and accelerometers that continuously tracked the vehicle's attitude and velocity. These instruments were good, but they drifted over time. Tiny biases in the gyroscopes, tiny scale factor errors in the accelerometers accumulated over the course of a 3-day trip to the Moon until the navigation errors could become dangerously large. The spacecraft also had a sextant, which allowed an astronaut to take sightings on known stars. These sightings were intermittent, only taken when an astronaut had time to perform the measurement, and they were noisy because the astronaut was a human being floating in a spacecraft, trying to align crosshairs on a distant point of light. But each sighting provided an independent check on the spacecraft's orientation and position. The Kalman filter fused these two sources of information. Continuously, it predicted the spacecraft's state using the inertial measurements and the known laws of orbital mechanics. Periodically, when a star sighting was taken, it incorporated that measurement, correcting the accumulated drift and tightening the covariance. The result was a navigation estimate far more accurate than either source of information could have provided alone. And the filter did all of this on the Apollo guidance computer, which had roughly 2 kilowords of erasable memory and ran at a speed that would embarrass the cheapest calculator you could buy today. The engineers at NASA's Ames Research Center, led by Stanley Schmidt, had to develop clever approximations to make the full Kalman filter computations fit within those absurdly tight computational constraints. They partitioned the state vector, simplified the matrix operations, found ways to get 95% of the optimal performance with maybe 20% of the computation. The gap between mathematical theory and engineering implementation, the act of making a beautiful algorithm work on an ugly little computer, is where the real art of engineering lives. And the Kalman filter worked. It navigated Apollo 8 around the Moon and back. It navigated Apollo 11 to the lunar surface. Think about what was happening during the critical phases of those missions. The spacecraft is hurtling through the void at thousands of miles per hour. The margin for error on re-entry is about plus or minus half a degree. Come in too steep, and the spacecraft burns up in the atmosphere. Come in too shallow, and it skips off the atmosphere like a stone off water and goes sailing into deep space with no way back. That's the difference between life and death, and it's measured in half a degree. And the thing keeping the navigation accurate enough to hit that window is a mathematical algorithm running on a computer with less memory than the chip in a modern greeting card that plays "Happy Birthday" when you open it. It navigated Apollo 13 home safely under conditions that no one had planned for, when an oxygen tank explosion crippled the command module and the crew had to use the lunar module as a lifeboat. The navigation problem became enormously more complicated than anyone had anticipated. The normal star sighting procedures were disrupted because debris from the explosion was floating alongside the spacecraft, glinting in the sunlight, making it nearly impossible to distinguish stars from debris through the sextant. The crew had to improvise, and through it all, the filter kept running, kept estimating, kept blending whatever measurements the crew could provide with its internal model of orbital mechanics. The filter didn't panic. It didn't get confused by the unprecedented situation. It just did the math, incorporating each new piece of information, updating its estimate, keeping track of its own uncertainty. Doing its job with quiet, mathematical reliability, while 3 human lives depended on it 250,000 miles from Earth. Today, the Kalman filter is everywhere. Your phone's GPS uses a version of it to estimate your position by fusing satellite signals with accelerometer data. Each GPS satellite is essentially telling your phone, "You're somewhere on a sphere of a certain radius centered on me." Multiple satellites give you multiple spheres, and the intersection of those spheres gives you a position. But the measurements are noisy, the signals bounce off buildings, the clock in your phone isn't perfectly synchronized. The Kalman filter takes all of these imperfect measurements, combines them with a model of your motion. If you were walking north at 3 miles per hour a second ago, you're probably still walking north at roughly 3 miles per hour now, and produces an estimate of your position that's better than any single GPS measurement alone. The autopilot on a commercial aircraft uses multiple Kalman filters, running simultaneously, to estimate the aircraft's state by blending data from inertial sensors, air data probes, GPS, and radio navigation aids. Self-driving cars use extended Kalman filters, or their more recent cousins called unscented Kalman filters and particle filters, to track the positions and velocities of nearby vehicles and pedestrians based on noisy radar and LiDAR returns. Financial models use them to estimate underlying market state variables from noisy price data. Weather prediction models use them to assimilate satellite observations into atmospheric models. Submarine navigation, satellite attitude control, medical monitoring systems, robot localization. The list goes on and on. It might be the single most widely applied result in all of control theory. And if you think about it in terms of language, the Kalman filter represents a profound evolution. Earlier control systems could only act on what they directly measured. The Kalman filter enabled them to infer things they couldn't measure, to fill in gaps, to see through noise, to maintain an internal model of reality that was richer and more accurate than any single sensor could provide. The machine wasn't just following instructions anymore. It was, in a meaningful sense, understanding its own situation. But understanding the present, even with the mathematical sophistication of the Kalman filter, is still not the same as planning for the future. And as control systems grew more ambitious, as they were asked to manage processes with tight constraints and competing objectives and complex interactions, a new question emerged. Could a controller look ahead? Could it anticipate what was going to happen, not just react to what had already happened? Could it, in some meaningful sense, plan? That question led to one of the most powerful control strategies ever developed. And its origins, oddly enough, aren't in a university lab or an aerospace program. They're in the humid, sprawling oil refineries of the Gulf Coast of Texas. If you've ever driven along the Texas or Louisiana coast, you've seen them. Refineries stretching for miles along the ship channel. Towers and columns and pipe racks silhouetted against the sky, lit up at night like industrial cities. These facilities take crude oil in one end and produce dozens of different products out the other. Gasoline, diesel, jet fuel, lubricants, petrochemical feedstocks. And the processes inside them are enormously complex. Hundreds of interacting variables, temperatures, pressures, flows, compositions, all changing simultaneously, all affecting each other. By the 1970s and 80s, these refineries were running thousands of PID controllers, each one managing a single loop. A temperature here, a pressure there, a level somewhere else. And they worked, after a fashion. But here's the issue. Each PID controller was acting independently. It didn't know what the other controllers were doing. And in a tightly coupled process, where changing the temperature in one column affects the pressure in the next column, which affects the flow to a third column, independent controllers fight each other. Controller A adjusts a valve to raise a temperature. That changes the pressure somewhere else. Controller B sees the pressure change and adjusts a different valve to compensate. But B's adjustment changes a flow rate that affects A's process. So A reacts again. And B reacts to A's reaction. And the whole system oscillates or settles into some compromised state that's stable but far from optimal. The refinery engineers wanted something smarter. They wanted a controller that could see the whole picture, that could consider multiple variables simultaneously, that could look ahead and plan a sequence of moves, like a chess player thinking several moves ahead, rather than reacting one move at a time, like a player who can only see the current board. And they wanted something that could respect constraints, real, hard, physical constraints. You can't heat a column above a certain temperature or the catalyst degrades. You can't exceed a certain pressure or the safety valve opens. You can't change the feed rate faster than a certain amount or you'll upset the downstream units. And you have product specifications to meet. Sulfur content must be below a certain threshold. Octane number must be above a certain level. These limits aren't suggestions. Violate them and you make off-spec product, or you damage equipment, or you create a safety hazard. Traditional PID control doesn't handle constraints gracefully. A PID controller just calculates its output and sends it to the actuator. If the calculated output exceeds what the actuator can actually do, the actuator saturates. It hits its physical limit, and the controller doesn't know. The integral term keeps winding up, building more and more corrective action that the actuator can't deliver. And when the situation finally reverses, the integral has accumulated so much memory that the system overshoots wildly in the opposite direction. Engineers developed workarounds for this, anti-wind-up schemes that detect actuator saturation and freeze the integral term. But these are patches, not solutions. What the refinery engineers needed was a controller that knew about the constraints from the start, that incorporated them into its decision-making, that would never try to do something the system physically couldn't do. And that's exactly what Model Predictive Control, MPC, provides. Here's how MPC works, and the idea, once you see it, feels almost obvious, which is usually a sign that it's genuinely deep. At every control step, the controller uses a mathematical model of the process to predict what will happen over a future time horizon. Maybe 30 steps ahead, maybe 60, depending on the application. Then it sets up an optimization problem. Given all the constraints, the valve limits, the temperature limits, the pressure limits, the product specs, find the sequence of control moves over that future horizon that minimizes some cost function. Maybe the cost function penalizes deviation from the set points. Maybe it penalizes excessive energy use. Maybe both. You choose what matters to you. The optimization produces a whole sequence of future control moves. But here's the clever part. You only execute the first one. Then you wait for the next measurement to come in. You update your prediction based on what actually happened, not what you predicted would happen. You shift your prediction horizon forward by one step, and you solve the whole optimization again. This receding horizon approach means you're constantly replanning. If your prediction was wrong, you don't blindly follow the original plan. You incorporate the new information and replan. It's like driving a car on a winding mountain road. You don't plan your entire route from start to finish at the beginning and then follow it with your eyes closed. You look ahead, plan for the next few curves, execute the first turn, and then look ahead again from your new position. If there's a rock in the road that you didn't see before, you adjust the plan. The earliest industrial MPC algorithms appeared in the late 1970s. Dynamic matrix control, developed by Charlie Cutler and Brian Ramaker at Shell Oil. Model algorithmic control, developed by Jacques Richalet and colleagues in France. These algorithms used simple models, just the recorded response of the system to a step change in input, and solved the optimization at each time step. Computationally expensive, yes, but the processes they were applied to were slow. Distillation columns and reactors that evolved over minutes or hours. There was time to solve the optimization between one control action and the next, and the results were impressive. When Shell deployed its dynamic matrix control at refineries along the Gulf Coast, the improvements were visible almost immediately on the trend charts in the control room. Variables that used to wander and oscillate under independent PID control settled down. Temperatures that used to swing by 10 degrees now held within 2. Flow rates that used to drift as operators made manual adjustments stabilized as the MPC took over the coordination. But the real impact wasn't just tighter control for its own sake. Tighter control means less variability. Less variability means you can operate closer to constraint boundaries, and operating closer to constraint boundaries means better economics. Here's a way to think about why that matters so much. Imagine you're driving a car on a road with a guardrail on each side, and you're trying to drive as fast as possible without hitting the rails. If your steering is wobbly, if you're swerving back and forth, you have to keep your average position well away from the rails to avoid hitting them during a swerve. You're leaving a big safety margin on each side. But if your steering is precise, if you can hold a tight line, you can drive closer to the optimal path in the center of the road, or even closer to one rail if that's where you get the best speed. The precision of your control determines how close you can get to the limits without violating them. If your product specification requires sulfur below 50 parts per million, and your old PID-based system had so much variability that you had to target 30 to make sure you never exceeded 50, MPC could tighten the variability enough that you could target 45 and still never violate the spec. That difference, running closer to the limit, translates directly into higher throughput, lower energy cost, better product yield. The payback periods on MPC installations were sometimes measured in weeks. Now, for decades, MPC was limited to slow processes because solving the optimization problem at every time step required serious computation. Refinery dynamics play out over minutes and hours. You had time. But as computers got faster, and they got faster at an astonishing rate, MPC became feasible for faster and faster systems. By the 2000s, processors were fast enough to solve MPC optimization problems in milliseconds. And that opened the door to applications with dynamics that played out in fractions of a second. Applications like autonomous vehicles. Think about what a self-driving car needs to do. Follow a planned path, maintain safe distances, stay in its lane, avoid obstacles, obey traffic rules, all while respecting the physical limits of the vehicle, the maximum steering angle, maximum braking force, tire grip limits that change with road conditions. And it needs to look ahead, to see the curve coming and start braking before it arrives, to anticipate the merge and adjust its speed accordingly. That's an MPC problem through and through. A model of the vehicle dynamics, a prediction horizon, maybe 2 or 3 seconds into the future. Constraints: maximum steering angle, maximum comfortable deceleration, lane boundaries, minimum following distance. A cost function that balances staying centered in the lane against smooth steering, against passenger comfort, against fuel efficiency. At every time step, the MPC solves this optimization, finds the best sequence of steering and braking and throttle commands for the next 2 seconds, executes the first command, and then replans from the updated position. And here's what makes this particularly challenging compared to refinery MPC. The environment is changing rapidly and unpredictably. Other cars are making decisions you can't predict. Pedestrians step off curbs, construction zones appear, traffic lights change. The MPC has to incorporate new information constantly and replan on the fly. It's not optimizing a slowly evolving chemical process over 30 minutes. It's optimizing a rapidly evolving driving scenario over 2 seconds, and it has to do it 20 or 30 times per second. Many of the motion planning and control architectures in autonomous vehicles today use some form of model predictive control at their core. MPC is also in building climate control systems, where the controller predicts the thermal behavior of the building over the next several hours, accounts for weather forecasts and occupancy schedules, and optimizes heating and cooling to minimize energy cost while keeping everyone comfortable. It's in wind turbines, where the controller adjusts blade pitch and generator torque to maximize energy capture while keeping structural loads within safe limits. It's in the electrical grid, where system operators use MPC-like approaches to schedule generation and manage transmission constraints across entire regions. And it's increasingly in transportation systems, where the optimization isn't just about controlling one vehicle, but about coordinating entire fleets. Researchers at places like MIT have been working for decades on exactly this kind of large-scale optimization, figuring out how to assign fleets of aircraft to flight schedules, how to reroute passengers when weather disrupts operations, how to balance the needs of airlines, who need to make a profit, with the needs of passengers, who need to get where they're going with minimal delay. These problems involve billions of possible decisions, and solving them requires the same blend of mathematical rigor and computational power that MPC uses at the process level. One researcher described her attraction to these problems in a way that I think captures the appeal of the entire field of control and optimization. She said she liked things that don't have a right or wrong answer, but that are amenable to rigorous, structured mathematics. She liked the uncertainty and messiness of real problems, but also the precision of the tools you use to attack them. That tension between the messiness of the real world and the precision of the mathematical language you use to manage it runs through everything we've talked about tonight. And here's a lovely detail that connects two threads of our story. In many modern MPC implementations, a Kalman filter sits right at the front end, estimating the current state of the system from noisy measurements and feeding that estimate into the MPC optimizer, which then plans the future trajectory. Kalman and MPC working together, the observer and the controller, estimation and optimization. One algorithm figuring out where you are, another algorithm figuring out what to do next. Two different mathematical languages, developed decades apart for completely different problems, fitting together as naturally as a question and an answer. But MPC, for all its power, is still working with a mathematical model. Someone had to write that model down. Someone had to identify the parameters. Someone had to make assumptions about the system dynamics, the disturbances, the constraints. And models are never perfect. The map is never the territory. Which brings us to the most recent chapter in this story, and arguably the most provocative. Because over the last decade or so, a new approach has emerged that challenges the very notion of human-designed models and human-designed controllers. An approach where the machine doesn't follow a program or a model that a human wrote. Instead, it learns its own strategy, from experience, through trial and error, through a process that looks, from the outside, an awful lot like the way a child learns to catch a ball. Machine learning. Two words that have generated an astonishing amount of excitement, anxiety, hype, and genuine breakthrough over the last decade. And the intersection of machine learning and control systems is one of the most fascinating and consequential developments happening in engineering right now, because it raises a question that goes to the heart of everything we've been talking about tonight. If a machine can learn to control a system without being explicitly programmed, without being given a model, without being told the equations of motion, without any of the mathematical language we've been discussing, then what was all that language for? Was it a temporary workaround, a crutch that we needed only because we didn't have enough data and enough computational power to let the machine figure it out on its own? Let's start with what machine learning actually offers in the world of control. Because the promise is genuinely remarkable. Traditional control design, everything we've talked about so far, follows a specific workflow. You start with a system. You build a mathematical model of it, either from physical principles or from experimental data. You design a controller based on that model, using the tools of classical or modern control theory. And then you implement the controller in a PLC or a computer and deploy it. Each step requires expertise. Each step can introduce errors, and the whole process assumes that your model is good enough to base decisions on. Machine learning, specifically a branch called reinforcement learning, offers a fundamentally different approach. Instead of designing a controller analytically, You let the machine learn one through experience. You define a reward signal, something that tells the machine whether it's doing well or poorly. And then you let the machine try things. Lots of things, millions of things. It takes actions, it observes the results. It adjusts its behavior to get more reward. Over time, through millions of iterations of trial and error, it develops a policy, a mapping from the current state of the system to the action it should take. No model required, no transfer functions, no state-space matrices, no Bode plots. Just data and computation, and a clearly defined objective. And in some applications, this approach has produced results that are genuinely stunning. In 2022, DeepMind, the artificial intelligence lab owned by Alphabet, published work on using deep reinforcement learning to control plasma in a tokamak fusion reactor. The plasma in a fusion reactor is one of the most challenging control problems imaginable. It's a superheated gas at over 100 million degrees, held in place by powerful magnetic fields inside a donut-shaped chamber. The plasma is inherently unstable. It writhes and shifts and tries to touch the walls of the chamber, and if it does, the fusion reaction collapses. Controlling it requires manipulating dozens of magnetic coils simultaneously, adjusting their currents in real time to shape and stabilize a mass of matter that's hotter than the core of the sun. The DeepMind team trained a neural network controller entirely in simulation. Millions of simulated plasma scenarios, each one slightly different, each one teaching the network something about how the plasma responds to different magnetic field configurations. And then they deployed the trained controller on a real tokamak, the TCV reactor in Switzerland. And it worked. The neural network managed to hold the plasma in configurations that would have been extremely difficult to achieve with conventional control methods. It was controlling something that no human had explicitly told it how to control. It had figured out the language of plasma dynamics on its own, through sheer computational experience. Or think about robotic manipulation. Teaching a robot to pick up objects, which seems trivially easy for a human, but is nightmarishly difficult to program explicitly. If you try to write a traditional control program for a robot hand picking up a coffee mug, you have to account for the shape of the mug, the weight, the friction between the fingers and the ceramic surface, the compliance of the gripper, the center of mass, whether the mug is empty or full. Change the mug to a soft plastic bag full of groceries, and your carefully programmed controller is useless. The physics of contact, of friction, of flexible objects and varying shapes and uncertain weights is enormously complex. Too complex to model analytically for every possible scenario. Labs at Berkeley and Stanford and various companies have shown robots learning to pick up novel objects they've never seen before, fold laundry, and insert components with precision finer than the thickness of a credit card, all through reinforcement learning, all without anyone writing explicit instructions for how to move the fingers and apply the forces. The robot discovers the strategy through millions of trials in simulation, gradually building a neural network policy that maps sensory input to motor commands. The resulting behavior can look remarkably fluid and natural, sometimes finding grasping strategies that human engineers wouldn't have thought of. So, here's the question. If machine learning can figure out how to control a tokamak plasma or a robotic hand, do we still need all that classical and modern control theory? Do we still need Bode plots and Kalman filters and PID tuning rules? Are they obsolete? Relics of an era when we didn't have enough data and compute to let the machine learn? The answer, and I want to be really clear about this because it matters, is no. Emphatically no. And the reason has everything to do with the language theme we've been following all night. Here's the problem with a neural network controller, and it's a deep one. When a neural network learns a control policy, what exactly has it learned? It's learned a mapping from states to actions that works well on the data it was trained on the scenarios it experienced during training. But what about scenarios it hasn't seen? Edge cases, rare disturbances, sensor failures, conditions that lie just outside the distribution of training data. A neural network gives you essentially no guarantees about what it will do in those situations. It might do something reasonable. It might do something catastrophic. And crucially, you often can't tell in advance which one it will be, because the internal workings of a deep neural network are notoriously difficult to interpret. Now, for a video game or a simulated environment, this isn't a big deal. If the AI does something weird, you restart the game. But for a fly-by-wire aircraft, or a nuclear power plant, or an autonomous car driving in traffic with pedestrians, it usually works, and we're not sure about edge cases is not an acceptable engineering standard. For safety-critical systems, you don't just need a controller that usually works. You need one that always works within defined bounds under specified conditions. You need guarantees. And guarantees are precisely what classical and modern control theory were designed to provide. Stability proofs, robustness margins, worst-case performance bounds. Lyapunov theory, which gives you mathematical certificates that a system will return to equilibrium after any disturbance within a specified set. H-infinity design, which gives you controllers that perform well under the worst-case disturbance. Ruth Hurwitz criteria, which tell you definitively whether a system is stable or unstable. All of these tools were developed to provide the kind of mathematical certainty that safety-critical systems demand. A learned controller, by itself, provides none of these guarantees. It's a black box. It works on training data, and you hope it generalizes. But hope is not an engineering strategy. Consider a concrete scenario. You've trained a neural network to control a chemical reactor. During training, the reactor temperature ranged between 200 and 400 degrees Fahrenheit. The network learned a beautiful policy for that range. But one day, due to an upstream upset, the feed composition changes in a way that was never seen during training. The reactor temperature starts climbing past 400 degrees Fahrenheit into territory the network has never experienced. What does it do? With a traditional PID controller, you know exactly what it does. It keeps pushing the cooling valve open proportionally harder as the error grows. The behavior is predictable, analyzable, guaranteed by the mathematics of the PID algorithm. With a neural network, you genuinely do not know. It might do something reasonable, it might do something bizarre, it might freeze, it might oscillate. And you can't find out without either testing it in that specific scenario or proving stability mathematically, which is currently very difficult for large neural networks. This uncertainty is why the thoughtful, productive work happening at the intersection of ML and control is about combination, not replacement. So what's actually happening in the most thoughtful and productive corners of the field is not a replacement of control theory by machine learning. It's a merger, a collaboration, and it's happening in several really interesting ways. One approach uses machine learning to build better models, and then uses those models inside conventional control frameworks. Remember how MPC needs a model? What if that model is partially learned from data? You might have a physics-based model that captures the broad strokes, the conservation laws, the known dynamics, and then use a neural network to learn the residual, the part that the physics model gets wrong, the unmodeled friction, the aerodynamic effects that are too complex to derive analytically, the subtle nonlinearities that show up at extreme operating conditions. This hybrid approach, sometimes called physics-informed learning, gives you the interpretability and extrapolation ability of a physics model, plus the flexibility and accuracy of a learned model. And then you wrap that hybrid model inside an MPC framework that handles constraints and provides performance guarantees. Another approach goes in the other direction. You let the neural network learn a control policy, and then you verify it using tools from control theory. Can you prove that this learned controller stabilizes the system? Can you find a Lyapunov function, that mathematical energy-like quantity that must decrease over time, for the closed-loop system with the neural network in the loop. This is an active area of research, and it's difficult because neural networks are complicated, non-linear functions. But progress is being made. Researchers at MIT and Stanford and other universities are developing methods to either verify learned controllers after the fact or to bake stability guarantees into the learning process itself, constraining the neural network during training so that the resulting policy is provably stable. And there's reinforcement learning with constraints, where the learning algorithm itself is designed to respect safety constraints during both training and deployment. Instead of just maximizing a reward signal, which can lead to all sorts of creative but dangerous behaviors as the agent games the reward, you add hard constraints that the agent must never violate. Keep the aircraft within its flight envelope, never exceed structural load limits, stay within the lane. This connects directly to the constrained optimization at the heart of MPC. And some of the most promising recent work essentially combines reinforcement learning with model predictive control, using learning to improve the model or the cost function, while using MPC's constraint handling machinery to ensure safety. There's a beautiful irony here if you step back and look at the arc of the whole story. The field of control theory spent decades developing rigorous mathematical tools for analyzing and designing feedback systems. Then machine learning came along and appeared to say, we don't need all that theory, we have data. And now, as machine learning pushes into safety-critical applications, autonomous vehicles, surgical robots, power grid management, aerospace, it's discovering that it needs exactly that theory. Stability analysis, robustness guarantees. The tools that Lyapunov and Nyquist and Bode and Kalman developed, the mathematical language that we spent the earlier part of this evening exploring. The data-driven approach and the model-based approach aren't rivals. They're complementary. The machine that learns from experience and the engineer who designs from understanding are both needed, and the most capable systems of the future will almost certainly use both, layered together, each covering the other's weaknesses. Machine learning providing the flexibility and adaptability that mathematical models lack. Control theory providing the guarantees and interpretability that neural networks lack. And this connects to a broader truth about engineering that one MIT professor captured perfectly when she described what drew her to her field. She said she liked things that don't have a right or wrong answer, but that are amenable to rigorous, structured mathematics. She liked the uncertainty and messiness of real problems, combined with the precision of mathematical tools. And she found that the most interesting work happened at the boundaries between disciplines, when people from different backgrounds, with different ways of thinking, came together to tackle problems that none of them could solve alone. That description fits the current state of control systems perfectly. The most interesting work is happening at the boundaries, between control theory and machine learning, between hardware engineering and software engineering, between optimization and safety, between the rigorous mathematical traditions of Kalman and Pontryagin and the data-driven pragmatism of neural networks and reinforcement learning. The people making the most progress are the ones who can hold multiple perspectives simultaneously, who can think like a mathematician when the problem calls for precision, and like an experimenter when the problem calls for exploration. And this brings us to something that I think is the deepest lesson in this entire story about language and machines. It's a lesson about the relationship between understanding and performance. Here's the thing that's easy to miss in all the excitement about machine learning and AI. When a neural network learns to control a plasma in a tokamak, it's not understanding the physics of plasma. It's finding a mapping from sensor readings to coil currents that happens to work. It doesn't know why it works. It can't explain its reasoning. It can't generalize to a different tokamak with a different geometry without being retrained. It's performing brilliantly while understanding nothing. And when a control engineer designs a PID controller using Bode plots and stability margins, they understand the physics of the system, the dynamics of the controller, the trade-offs between performance and robustness. They can explain every design choice. They can predict what will happen if conditions change. They can generalize to similar systems with confidence. They're performing competently while understanding deeply. Performance and understanding are not the same thing. And one of the recurring themes in the history of science and engineering is the tension between them. Sometimes you need performance. You need to get the job done, and understanding can come later or not at all. And sometimes you need understanding, because understanding is what lets you handle situations you've never seen before, what lets you know when something is about to go wrong before it actually goes wrong. What lets you build not just a system that works, but a system you can trust. The languages we've talked about tonight, all of them, from the earliest relay logic to the most sophisticated reinforcement learning algorithms, are attempts to bridge this gap. Relay logic is pure understanding, every connection explicit, every decision visible, but limited in performance. Machine learning is, potentially, pure performance, capable of extraordinary feats, but with limited transparency and understanding. And the richest, most capable systems are the ones that combine both. That use mathematical understanding to set the boundaries and provide the guarantees, and use learned adaptation to achieve performance within those boundaries. This pattern, this layering of understanding and performance shows up everywhere you look in modern engineering. An autonomous vehicle has neural networks doing perception, recognizing pedestrians and reading traffic signs, performing tasks that would be nearly impossible to hand code. And underneath those neural networks, providing the safety net, are classical control systems enforcing hard limits on acceleration, on steering rate, on following distance. The neural network handles the complexity. The classical controller handles the safety. Both languages working together. A modern aircraft has flight control computers running sophisticated multivariable controllers with gain scheduling, adapting to changing flight conditions. And those computers are wrapped in layers of redundancy, with multiple processors running different software designed by different teams, so that a single failure in one language, one software implementation, doesn't bring down the entire system. And underneath all of that, there are often simple analog backup systems, the most basic possible language of direct mechanical linkage that can still fly the aircraft if every computer fails. Your car, which you probably think of as a simple mechanical device, contains dozens of control systems working simultaneously. The engine management system adjusts fuel injection and ignition timing thousands of times per second. The electronic stability control monitors your steering angle, your speed, and the individual rotation rates of all four wheels. And if it detects that the car is beginning to skid, it selectively applies braking to individual wheels to bring you back on course. Studies estimate that electronic stability control reduces single-vehicle fatal crashes by about 30%. That's tens of thousands of lives saved every year by a control system that most drivers don't even know exists. The best controllers are the ones you never notice. They do their work silently, making you feel like a better driver than you actually are. Even in a PLC on a factory floor, you see this layering. The main program, running in ladder logic or structured text, handles the normal operation. But separate safety circuits, often implemented in a dedicated safety PLC with redundant processors and certified safe programming, handle the emergency stops and protective interlocks. The normal operating language and the safety language are deliberately kept separate so that a bug in the operating program can't compromise the safety system. And I think this pattern of layered languages, of systems that combine understanding and performance, transparency and capability, simple and sophisticated, is not just an engineering pattern. It's a deep pattern in how effective systems of any kind are organized. Your body does it. The fast, unconscious reflexes that pull your hand away from a hot stove operate on a different language than the slow, conscious deliberation that decides whether to take a job offer. Both are necessary. Both operate simultaneously. and the system works best when each layer does what it's best at, without interfering with the other. So, where does this leave us? We've traveled a long way tonight. From relay panels clicking in the dark to neural networks controlling plasma at 100 million degrees. From an electrician's familiar ladder diagram to a mathematician's state-space matrix. From a simple float valve in an ancient water clock to a model predictive controller optimizing a refinery in real time. And through all of it, the central challenge has been the same. How do you take what a human wants and turn it into something a machine can do? How do you bridge the gap between intention and execution? How do you translate? Every language we've discussed is an attempt at that translation. Relay logic translated human intention into physical wiring. Ladder logic translated it into a visual program that electricians could read. Structured text translated it into a format that programmers could work with. HMIs and SCADA systems translated machine status back into visual information that operators could act on. Transfer functions and Bode plots translated system dynamics into a mathematical form that engineers could analyze and design with. PID translated the abstract concept of error correction into 3 concrete, implementable terms. State-space models translated complex, interacting systems into compact matrix equations. The Kalman filter translated noisy, incomplete measurements into the best possible estimate of reality. MPC translated future planning with constraints into a solvable optimization problem. And machine learning translated raw experience into executable policy. Each language solved a problem that the previous languages couldn't handle. And each language created new problems, new gaps, new limitations that the next language would need to address. The tower kept growing, each floor built on the one below it, each floor adding capability and complexity. And the tower is still growing. Right now, tonight, there are researchers working on problems that don't even have names yet, trying to find new ways to make machines understand our intentions, new ways to make machines explain their actions to us, new ways to combine the best of human understanding with the best of machine performance. The language is still evolving, and it will keep evolving as long as there are systems to control and humans who want to control them. And now, here's where I want you to let the details soften. Let the names fade if they want to. Bode and Nyquist and Kalman and all the rest, they'll be there if you ever want to come back to them. Let the differential equations and the state-space matrices blur into the background. They're not going anywhere. What I want you to carry with you, as you settle deeper into wherever you are tonight, is the shape of the story, the arc of it. Humans found machines useful. Machines did what physics made them do, which wasn't always what humans wanted. So humans invented ways to tell machines what to do. First with wires, then with code, then with math, then with data. Each new language opening up possibilities that the previous one couldn't reach. Each new language bringing its own limitations, its own blind spots, its own need for the next language to come along and fill the gaps. And the beautiful thing, the thing I find genuinely comforting when I think about it, is that all of these languages are running right now. All of them. Simultaneously, in layers. Right now, somewhere, a relay is clicking in a safety circuit, providing the most basic, most reliable, most physically direct form of control there is. A normally closed contact, wired in series with a motor contactor. If the emergency stop button is pressed, the contact opens and the motor stops. No software, no computation, no possibility of a software bug or a logic error. Just physics. The oldest language, still doing its job. Right now, somewhere, a PLC is scanning through its ladder logic program, reading inputs, evaluating rungs, setting outputs. 100 times a second. Keeping a conveyor running at the right speed. stopping a press when the guard door opens, counting parts and tracking batches. The language that Dick Morley's team invented in the late 1960s, still going strong, still the backbone of manufacturing worldwide. Right now, somewhere, an operator is glancing at an HMI screen, seeing a color change, noticing a trend moving in the wrong direction, reaching for a radio to call the field technician. The machine speaking to the human, in the visual language of gauges and colors and alarm banners. The human listening, interpreting, deciding. Right now, somewhere, a Kalman filter is fusing GPS signals with accelerometer data in your phone, estimating your position to within a few meters. Another Kalman filter is doing the same thing in the navigation computer of an aircraft overhead. Another one is running in a submarine somewhere in the ocean, estimating the vessel's position from inertial sensors that haven't been corrected by GPS in days, because submarines can't receive GPS signals underwater. Right now, somewhere, an MPC controller is looking 5 minutes into the future of a chemical reactor, solving an optimization problem, finding the sequence of valve adjustments that will bring the temperature to set point without exceeding the pressure limit, and executing the first of those adjustments. One step at a time, constantly replanning, constantly incorporating new measurements, looking ahead and adjusting. Right now, somewhere, a neural network is processing camera images from a car driving down a highway, identifying lane markings and other vehicles and pedestrians, generating a representation of the world that feeds into a motion planner, which feeds into a trajectory optimizer, which feeds into a low-level vehicle controller that adjusts steering and braking and throttle, keeping the car safely in its lane while its human occupant listens to the radio and thinks about dinner. All of these systems, all of these languages, all running simultaneously, all layered on top of each other, all depending on each other. The simple ones providing the safety foundation that the complex ones are built upon. The complex ones providing capabilities that the simple ones could never achieve alone. And there's another domain where the language of control shows up in a way that's visible to anyone who's been to a concert or a theater or a house of worship or a corporate event. Stage lighting. The lights that create atmosphere, that focus attention, that transform a bare stage into a moonlit forest or a neon-soaked nightclub. Those lights are controlled by systems that share surprising DNA with the industrial PLCs and SCADA systems we've been discussing. A modern lighting console, something like the Onyx system manufactured by Obsidian Controls, is essentially a specialized control interface. It takes human artistic intent. I want this scene to feel warm and intimate, with a slow crossfade to cool blue when the music changes, and translates it into a protocol called DMX, which sends numerical values to hundreds of lighting fixtures simultaneously. Each fixture might have dozens of controllable parameters: intensity, color, beam angle, position, speed of rotation, gobo pattern. And the console manages all of these parameters across all of these fixtures, organized into cues and sequences and playback faders. The parallels with industrial control are striking. The lighting console has programming views where you set up your fixtures, assign them channels, create groups, much like patching I/O on a PLC. It has playbacks, which are like the outputs of a control system, each fader controlling a different output to the stage. It has timing and transitions, which function like the timers and sequences in a PLC program. And it has pages and banks of presets, allowing the operator to organize hundreds of different lighting states in a way that's quickly accessible during a live performance. The language of lighting control is different from the language of industrial automation in its vocabulary. It's artistic rather than technical objective, but the grammatical structure is remarkably similar. Inputs, the operator's artistic decisions, the music, the stage action, are processed through a programmed logic, the cue list, the effects engine, and translated into outputs, DMX values to fixtures. And the operator, sitting at the console during a live show, is doing something very similar to what a SCADA operator does in a refinery control room, monitoring the current state of a complex system, making adjustments in real time, anticipating what needs to happen next, and executing changes smoothly and precisely. The difference, of course, is that in a refinery, a mistake might cause a safety hazard. In a theatre, a mistake might cause an awkward moment. The stakes are different, but the cognitive process, the human-machine conversation, is the same. And none of these systems demand your attention. None of them ask you to understand them. Just working, quietly, reliably, in the background of your life, making sure the temperature stays where it should, making sure the pressure doesn't exceed what's safe, making sure the airplane follows its flight path, making sure the water is clean and the power grid is stable and the elevator stops at the right floor. The world is full of these quiet conversations between humans and machines. Conversations that started with copper wire and evolved into code and evolved into mathematics and evolved into data. Conversations that happen millions of times a second, all around you, all the time, holding the infrastructure of civilization in place. And the people who made these conversations possible, the people who do this work every day, they're a fascinating blend of disciplines. A controls and automation engineer, as one practitioner put it, needs to have enough mechanical or chemical knowledge to understand the process being automated, enough electrical engineering knowledge to design and troubleshoot a control panel, enough software skill to write functional, readable PLC code, and enough IT knowledge to handle industrial networking. It's a role that sits at the intersection of multiple engineering fields, drawing from each one without fitting neatly into any single traditional discipline. Some of these people came to the field through electrical engineering, some through mechanical, some through computer science, some through chemical engineering, and many, honestly, came to it through a combination of formal education in one area and on-the-job learning in the others. The field of controls and automation tends to attract people who like variety, who enjoy the challenge of integrating different types of knowledge, who are comfortable with the messiness of real-world systems that don't behave exactly like the textbook equations predict. And there's a whole ecosystem of tools that these engineers carry with them. Digital multimeters for measuring voltages and currents in live circuits, wire strippers and terminal screwdrivers, specialized tools for the delicate work of terminating small-gauge wires in tight control panels, portable 24-volt power supplies, so you can power up the low-voltage side of a panel for troubleshooting without energizing the high-voltage side and putting yourself at risk. Voltage pens, simple devices that beep and flash when held near a live wire, providing a quick safety check before you start pulling connections apart. Because in a control panel where low-voltage DC circuits might be right next to high-voltage AC power feeds, knowing which wires are energized and which aren't isn't just good practice, it's a matter of personal safety. And of course, laptops. Beefy laptops with enough memory and processing power to run the PLC programming software, the SCADA development environment, and possibly a simulator, all at the same time. These aren't your typical consumer laptops. They need solid-state drives for reliability, plenty of RAM to handle the software, and multiple Ethernet ports for connecting to different networks simultaneously. And the PLC landscape itself is evolving in interesting ways. While the giants of the industry, Allen Bradley, Siemens, ABB, Beckhoff, continue to dominate the large-scale industrial market, newer, more accessible platforms are emerging. Arduino, the company known for inexpensive hobbyist microcontrollers, now makes a device called the Opta, which is a proper PLC with industrial ratings, relay outputs, programmable inputs, and support for the standard IEC programming languages. For about $200, including a permanent software license, someone can start learning PLC programming on real industrial hardware. That's a fraction of what a traditional PLC development kit would cost. And it clips onto DIN rail, just like its bigger industrial cousins, and it can be expanded with additional I/O modules that communicate through the same type of industrial protocols. This democratization of control hardware means that more people than ever can learn to speak the language of machines. A student in their apartment can set up a small DIN rail panel, wire up some sensors and actuators, program the PLC in ladder logic or structured text, and see the same fundamental principles at work that run the largest factories and refineries in the world. The scale is different, but the language is the same. The laptop in particular has become the controls engineer's primary tool. Every PLC manufacturer has its own software environment for programming their PLCs, and these environments range from simple and intuitive to complex and resource-hungry. The engineer's laptop is, in a very real sense, their translator. It's the device they use to convert their understanding of the process, their knowledge of control theory, their creative problem-solving, into the specific language that the specific PLC understands. And then they download that translation into the PLC, go out to the field, and watch to see if the machine does what they intended. These engineers, these translators between the human world and the machine world, are in demand everywhere. Manufacturing, oil and gas, pharmaceuticals, food and beverage, water treatment, power generation, building automation. Every industry that uses machines needs people who can speak to those machines. And because the field is relatively niche, because not many universities offer a dedicated degree in controls and automation, the people who develop these skills often find doors opening for them across a remarkable range of industries and companies. All of them. Every single one of these engineers and electricians and technicians, past and present, were doing the same thing at bottom. They were trying to find the right words, the right language, the right way to tell a machine what they wanted it to do, and to understand what the machine was telling them in return. That's a deeply human endeavor. Finding the right words. It's what poets do, and diplomats, and parents trying to explain the world to a child. The languages are different, the audiences are different, but the fundamental act, the reaching across a gap of understanding to make yourself known, that's the same everywhere. And tonight, the machines are listening. They're reading their sensors and executing their programs and adjusting their outputs. They're maintaining the temperature in this room. They're regulating the voltage in the power grid that's keeping your device running. They're controlling the water pressure in the pipes in the walls around you. All speaking their various languages, all following their various instructions, all doing what someone, somewhere, found a way to ask them to do. You don't need to understand any of it right now. The conversations will continue without you. The relays will click. The PLCs will scan. The Kalman filters will estimate. The MPC controllers will optimize. The neural networks will process. All of it will keep running, steady and patient, while you rest. So let that thought settle. Let it be a quiet, steady presence in the back of your mind as you drift. The world is held together by languages you can't hear, spoken by machines to machines, designed by humans who cared enough to find the right words. And those words are working, right now, all around you, as reliable and as invisible as gravity itself. The machines are talking, in languages that were invented by people who cared deeply about getting the translation right. People who sat in front of relay panels, listening to the clicking, learning the sound of normal. People who sat at PLC programming terminals, watching their ladder rungs execute for the first time, holding their breath to see if the motor would start. People who stood in mission control at NASA, trusting a Kalman filter on a tiny computer to bring 3 astronauts home through a corridor half a degree wide. People who sat at Shell Oil, watching their MPC controller tighten the variability on a distillation column, knowing that every degree of tighter control meant money saved and safety improved. People who trained neural networks on simulated plasmas and then held their breath as the algorithm took control of a real tokamak for the first time. All of them, every one, trying to find the right words, the right language, the right way to close the gap between what a human wants and what a machine can do. And finding it. Imperfectly, incrementally, but finding it. And the languages they found are working right now, all of them, all around you, as steady and as patient as gravity. So let that thought settle. Let it be the last thought you carry as you drift towards sleep. The world is held together by conversations you can't hear. And the translators, the engineers and electricians and mathematicians and programmers have done their work well. Everything is under control. Just breathe and rest.